Hi, I'm Tim Dr. T. Shamillard, and I'll be your instructor for this course. I'm an associate professor in the computer science department at the University of Colorado at Colorado Springs, where I teach a variety of game design and development courses, and I sometimes teach some computer science courses as well. I'm also the program director for our Bachelor of Innovation in Game Design and Development. I have 5.5 years of indie game development experience in a company called Peak Game Studios that I started with my 2 sons, and now I do my indie game development in my one-man shop, Burning Teddy. This is a 4-week course, and the graded work in the course consists of 3 automatically graded programming assignments in weeks 1, 3, and 4, and each of those is worth 25% of your grade. And then there's a quiz in week 2 that is also worth 25% of your grade. I've given you a number of exercises that aren't worth any points, but are good practice as you engage with the material in the course. And I've also given you some optional Unity projects that are also not worth any points, but are great practice as you interact with the Unity game engine and your C# code. In week 1, we'll do the Getting Started lesson, which you're doing right now, and you'll learn about selection, which lets us make decisions in our code. In week 2, you'll learn how to get player input in the Unity engine using a variety of different devices. And then in week 3, you'll learn about iteration, which is commonly called looping. In the final week, you'll learn about arrays and lists, and you'll also have a short finishing up video to watch. I wrote a book that we use in the first 2 C# programming and Unity courses at UCCS, and I've given you a free copy of that book in a week 1 reading. Thank you for taking this course. We'll use material from that book in all 4 courses in the specialization. Because this course is the second course in the specialization, it builds on the foundation that you built in the previous course. This course is based on the middle third of the first Programming with C# and Unity course we have at UCCS. If you run into trouble, because we're still learning to program, so we're still going to run into trouble, you can always post on the forums, and you can also go to the internet to try to find answers to your questions. Just like in the previous course, I've provided a course topic index that you can click on a particular topic and it will take you to the appropriate place in the appropriate video so you can review where I covered that topic. Okay, let's go get to work. In this lecture, you'll learn how to navigate one of my courses on Coursera. And although this is almost definitely not the course you're currently enrolled in, that doesn't really matter. All my courses on Coursera pretty much look the same. Let's go wander around the course. This is the home page for the course. So typically the first place people will go will be to Overview, and you can just click there. It's already highlighted, as you can see. And let's take a look at week 1. So week 1 of this course has a description of what you'll learn about in this module. I will use the terms module and week interchangeably in these courses. There's a set of learning objectives for this particular week. So in week 1, we have the Getting Started lesson and the Your First C# Code lesson. And each of these lessons has a set of videos and perhaps some readings and sometimes some additional stuff. So if I go to a particular video, like this one, obviously you can watch the video, but I also want to point out that there's a drop down here that you can click, and you can see there are a number of things you can download. You can download the actual video, you can download the subtitles and a transcript, and you can download the PowerPoint slides for the video. And finally, you can download a zip file of the code I generated as part of the lecture. And this is the piece that a lot of learners seem to miss, is that you can actually download the code when I've generated code in a lecture. So be sure to do that if you want to explore more from within Visual Studio how that code actually works. Okay, back to week 1. And I'll scroll down again to show you that at the end of week 1, you actually have a programming assignment, and you can go and complete that programming assignment. If you click on it, there are instructions for the assignment. It's often the case that you'll have some materials to download as well, and it's also often the case that you need either Windows materials or Mac materials, depending on which operating system you're using for the course. When it's time for you to submit, you click the My Submissions tab, and then you create a submission and you upload the appropriate file and so on. And eventually you get a grade, and you can look at the grader output by clicking Show Grader Output and viewing grader feedback. And then you get to see that, hey, you passed test cases, and that's awesome. And each of the other weeks are structured in a similar way. You can always go look at your grades in the course by clicking Grades over here on the left. And as you can see, I've passed everything and gotten 100% on everything, so that's great. That should give you confidence that I'm your instructor for the course. There are discussion forums for the course, and you can pick a forum. And when you pick a particular week, before you post, I will say you can click this drop down, and if you want to talk specifically about an assignment in that week, you should pick the assignment as the sub-forum that you want to post to. But learners can usually figure out what you're posting about by the contents of your post, but it's always better to pick the right sub-forum for whatever you want to talk about. In several of my courses, I actually have a resource here called the Course Topic Index. And if you click on the Course Topic Index, this is like a book index. You can look up a particular topic, and then you can click a link that will lead you to the appropriate place in the appropriate video that talks about that particular topic. And then you can just click play to hear the discussion in the video about that particular topic. And really, that's all there is to navigating one of my Coursera courses. You'll probably spend most of your time in specific weeks of the course, but there are other sections you can explore on the left as well. And there you go. That's how you navigate one of my courses on Coursera. This is the totally optional, don't watch it if you don't want to, Meet the Instructor lecture. I'm Tim, Dr. T. Shamillard, and I grew up in a small town in southeastern Massachusetts named Norton. And after high school, I went off to Georgia Tech to pursue a bachelor's in electrical engineering degree, but I was only at Georgia Tech for a year. So if you'd like, pause the video and guess for why I only stayed for a year, and then continue. As one of my past students said, I left for the love of a good woman. So my girlfriend was in Massachusetts, Georgia Tech is in Atlanta, Georgia, and that was too far for me. So I spent about a year and a half putting stuff into boxes and handing it to the UPS guy. And then I enlisted in the U.S. Air Force, went off to basic training, went to technical training school, and after about 4 months in the Air Force, I got married. So pause the lecture again if you'd like to decide whether that was the same girl I left Georgia Tech for or somebody else. The answer is, it is in fact the same woman, and we are still married. So here we are in the Air Force. We went off to Omaha, Nebraska for our first tour, and then after 16 months, the Air Force decided to send me to school full-time to pursue a bachelor's degree in electrical engineering at Georgia Tech. So I did get to finish that degree at Georgia Tech in electrical engineering. And then I went off to officer training school and got my commission as an Air Force officer. Our first assignment in the Air Force was at Los Angeles Air Force Base, where I spent 4 years managing contractors writing software to help us fly satellites. Particularly orbital software was my general area of expertise. We had our first 2 children, both boys, while we were in Los Angeles. and I also pursued my master's degree in computer engineering at the University of Southern California, going to school night. Finished that tour after 4 years and went off to the U.S. Air Force Academy, where I taught undergraduate computer science courses for 2 years. Now, the Air Force Academy is usually a 4-year tour, but I only spent 2 years there. So if you'd like to pause the lecture video again and try to guess why I only spent 2 years, go ahead and do so. The answer is the Air Force decided to send me off to UMass Amherst to pursue a doctorate. So I am in fact a doctor of computer science, so I don't actually help people. And my entire family loved the part in Treasure Planet, the movie, where there's a non-medical doctor and he is trying to help somebody who's injured, and he says, "I just sit here and I'm useless." And I saw that movie with my entire family at the movie theater, and at that line, every single person leaned over and looked at me. So everyone knows I'm a doctor, just not a real doctor. Okay, so I finished off that degree and went back to the Air Force Academy for that full 4-year tour that I should have had in the first place. And then my final assignment was to Washington, D.C., where I spent a couple of years managing contractors, developing web applications, and the databases that support those web applications. And then I retired from the Air Force. So I've been at the University of Colorado at Colorado Springs since 2003, and I've taught a variety of courses, including graduate-level software engineering courses, undergraduate computer science courses, and undergraduate game design and development courses, all of which I created from scratch. And in fact, we now have a Bachelor of Innovation in Game Design and Development, and I teach many of the beginning and the final course in that particular program, and I'm the program director for that program. So at this point, I exclusively teach game development courses. I also spent a year and a half as an indie game developer in a company that I formed with my 2 sons, and that's Peak Game Studios. And we did a number of games both on speculation and on contract. So here are the games we built on speculation. The 2 images on the left are a game called Ket that's based on an actual board game. So we got the license from the board game manufacturer. And you can think of this as chess with lasers. And you can actually download a free version of this game at this point from the Burning Teddy website. I'll talk about Burning Teddy soon. The other screenshot from the upper right is for a game that we didn't quite finish as we shut down the company once my sons sort of grew up and moved on to do other things. And that game is called Battle Paddles. And you should think of this as Pong with weapons, because that's sort of the big idea behind that game. We didn't quite finish it, but we'll get back to that game as well. So on this slide are the games that we built under contract. So as a company, we went and we got a contract to build some games, and we actually got paid to build them, and that was awesome. So the 2 on the left are for educational games for 8th graders. The one all the way to the left was a set of 4 mini games to teach about physics. And the title of that group of mini games was Physics with Neat Details. And if you think of the acronym for that, it's PWND. And so, of course, a little tongue-in-cheek game development, of course. And the lower one was to teach 8th graders about robotics. So they would configure a robot with various attachments to go complete a number of missions. Again, there were a few mini games to do. The upper right one is something called Colorado History Arcade. We got a contract to teach 4th graders about Colorado history, and that game was deployed on the Pikes Peak Library District website. So all of the games we built as a company, except for the Colorado History Arcade game, were using C#. We happened to use XNA Game Studio to do that. But now, of course, we've moved on to Unity. The company hasn't, but I have. And so that brings us to this next slide, where I tell you I now have a small company, and by small I mean just me, called Burning Teddy. And I use that company to publish textbooks and online courses and of course also to do game development. So that Battle Paddles game that I showed you the screenshot from, I am in the process of porting that over from XNA Game Studio to Unity. That is about 60,000 lines of code, so it's going to take a little while to port, but at some point that will be on the Burning Teddy website, burningteddy.com. And I'm also working on another smaller casual game that is called Balloons Extreme, and I'll actually post my progress on burningteddy.com as I build that game in Unity. So Burning Teddy, all the game development I'm doing is actually in Unity. So when I'm not teaching and I'm not doing game development, what am I doing? Well, a number of different things. But one of those things is cycling. So riding a bike is one of my joys in life, I guess. So these are my 3 bikes. The blue one is the oldest one, and that's really an old bike at this point. But I used it to really get into cycling, not racing so much, but doing long rides like a number of centuries, which are 100-mile bike rides, including at the time one of the 10 toughest centuries in the United States. And so that century had over 10,000 feet of climbing. That's what makes 100-mile bike ride harder than another is, elevation gain. And so I did a number of bike rides. The mountain bike, the one on the bottom, is a result of going mountain biking with some friends one day, and I loved it so much that I went out and bought the mountain bike the next day. The bike all the way on the right is my triathlon bike. So, being a cyclist, I did a lot of long rides. I also did a bunch of running, including a number of marathons and a running race that goes from the bottom to the top of Pikes Peak here in Colorado Springs. I did that running race multiple times. And once you've biked a long time and run a long time, you say, well, you might as well do some triathlons as well. Just add a swim and you'll be fine. And so I've done a variety of triathlons, all the way from sprint distance, which are really short, all the way up to an Ironman distance race. I also play guitar. I started doing that way back in high school and then gave it up for decades while I was raising my family and doing other things. And now I've started up again to try to learn how to do it even better than I used to. So moving from left to right, the acoustic is a Yamaha acoustic that I bought way back while I was just out of high school. The next guitar is a Joe Strummer replica. Fender came out with a Joe Strummer tribute guitar some years ago, and that was my starting point. But I replaced the 3-saddle bridge with a 6-saddle bridge because that's what Joe Strummer used. I got that relict pick guard from a place called Extreme Creations, and I even took the stickers that were on Joe Strummer's guitar and cut them into the shapes that they were worn into by the time Joe stopped playing the guitar, and affixed them to the guitar in the appropriate places. The next guitar is a Gibson Les Paul Gold Top from a couple of years ago. And the one all the way on the right is my most recent guitar. That is a Fender Stratocaster American Professional 2. And I didn't have a Strat, so I wanted a Strat. But I also couldn't resist getting it in the gorgeous Miami blue color. Really, the other thing, other than, interesting, like, reading books and stuff like that, the other leisure thing I do is I play video games. That should come as no surprise to you. And so the question is, what kind of video games do I play? And you should pause the video, guess in your mind what those might be, and then you can move on to see a screenshot of what I use to play my video games. You can see racing games are my passion, so really racing simulations, so, realistic racing games rather than arcadey racing games. And if you're interested in all the details of that racing rig, you can go to the PDF that I've provided as a resource for this lecture. So there you have it. None of this has anything to do with course content, but it gives you a little more insight into who's teaching you in the course. What will you learn about in this lesson? You'll learn about the bool data type and Boolean expressions. You'll learn about the selection control structure, which lets us make decisions in our programs. You'll learn about the if statement and the switch statement, which is the way that we implement the selection control structure in C#. You'll learn how to implement timers, which are useful in lots of different places in our games. You'll learn how to add spawners to your games, and you'll learn about tagging, which may not be what you think it is. In this lecture, you'll learn about Booleans, and Booleans can only have two values, true or false. Now there's a whole algebra built around this idea called Boolean algebra, but for our purposes, what we need to know is Booleans really help us as we make decisions in our code. We actually get a data type in C#, and that data type is called bool. And you've actually seen the bool data type before. Remember, the dec empty property returned a bool, and variables that are of type bool, or methods that return type bool, or properties that return type bool can only have the value true or false. The other thing we get related to Booleans is Boolean expressions. And Boolean expressions help us evaluate more complicated conditions than just checking the value of a variable. So we build up these Boolean expressions, but Boolean expressions can also only evaluate to true or false. How do we build up a Boolean expression? One way we build up a Boolean expression is by using logical operators. The first logical operator we'll talk about is AND, which is expressed using ampersand in C#. The way AND works is, let's say we have two Boolean variables, A and B. The only way that A ampersand B evaluates to true is if they both, A and B, are true. In other words, A and B is true. If A is false, or B is false, or both of them are false, the AND operator, or the AND operation, evaluates to false. The next logical operator we'll talk about is OR, which is those two vertical lines there. And OR works so that if either A is true, or B is true, or both are true, then the OR operation evaluates to true. So the only way OR evaluates to false is if both A and B are false. The final logical operator we'll talk about is NOT. So NOT is negation, and it's actually a unary operator. It doesn't take two operands, it only takes one. So let's say we're going to evaluate not A. If A is true, not A is false, and if A is false, not A is true. Now, those three operators may feel really strange to you, right? If you haven't done Boolean logic before, these seem sort of foreign, but as we practice building our Boolean expressions to help us make decisions in our code, you'll get more comfortable with how to build those Boolean expressions using the logical operators. The other kind of operators we regularly use as we build our Boolean expressions are called relational operators because they evaluate the relationship between two operands. So equal, which we check with two equals, not one, so we use equal equal, so we could check if name equal Bob, or if 1 equal 2, for example, which by the way, that second one would definitely evaluate to false. So equal checks for equality and only evaluates to true if those two operands are equal to each other. The next one, exclamation point equal, is not equal. So this does the opposite of equal. So not equal evaluates to true if the operands are not equal. So in other words, 1, exclamation point equal 2 evaluates to true because 1 is not equal to 2. Not true. It's not equal to true either. 1 is not equal to 2. And we have less than or equal, greater than, and greater than equal as the other relational operators that we can use to build our Boolean expressions. To recap, in this lecture you learned that Boolean expressions and Boolean variables are really useful to us as we make decisions in our programs, and you'll see how that's actually true in the next lecture. And you also learned that we get both the bool data type and Boolean expressions in C#. In this lecture, you'll learn how to use the selection control structure to make decisions in your code. And the C# mechanism that we'll use to implement that control structure is called the if statement. So what kind of decisions might we want to make in our code? We might need to decide how to move the player's avatar based on player input. We might need to decide whether an enemy drops loot or not. We might need to determine whether the player has leveled up. We could even try to determine which menu to go to based on the player's actions, and lots more. Our games are filled with lots of decisions, and we make those decisions in our code using the selection control structure. This is a pictorial representation of how an if statement works, and this is actually called a control flow graph because it graphs the flow of control through our program. The node at the top has a Boolean expression, in this particular case GPA greater than or equal to 3.0. And as you know, Boolean expressions evaluate to true or false. If the Boolean expression evaluates to true, we follow the true branch, the branch on the left, and we do whatever code we've included on that branch. And then we move on and follow the bottom arrow and sort of move on through the rest of our program. If the Boolean expression evaluates to false, we follow that false branch, which doesn't do anything, and just continue past the if statement in our code. Let's see how this actually works in C#. This is the code we'll start with, and all I've done at this point is I've added some documentation comments to the code, and I've added some code that prompts for and gets some user input. So the prompt is pick up the shiny thing, and the user is supposed to enter 1 for yes or 2 for no. After the prompt, the user will type something in and press enter, and console readline will return that string, which will then parse into an integer and put into our answer variable. None of this is the selection control structure or if statements. The if statements come in when we go to print an appropriate message. The format of an if statement is we put the keyword if, and then we put a Boolean expression between parentheses, and then we put the body of the if clause between curly braces. So if whatever Boolean expression we put here evaluates to true, we'll go execute the code in between this open curly brace and this closed curly brace. If the Boolean expression we put here evaluates to false, we'll just skip past the if statement and move on to the next line of code. So our Boolean expression will be, let's print a message if their answer is yes. So here's my Boolean expression. It evaluates to true or false. You should note that this is 2 equal signs. It's not 1 equal sign, it's 2 equal signs. This isn't an assignment. This is a relational operator. It's a comparison of the value of our answer variable and the integer literal 1. So if the user enters 1, this Boolean expression will evaluate to true and will go here. So let's print an appropriate message. And I'll say, you have the shiny thing. That seems like an appropriate message if the user has entered yes, they want to pick it up. So when I run the code, if I enter 1, it prints the "you have the shiny thing" message because the value of the answer variable is 1, so 1 is in fact equal to 1. If I run the code again and I enter 2, it doesn't print that message because the Boolean expression evaluated to false. So we've printed an appropriate message if they answered 1. What if they answer 2? Now it may be the case that we actually want to do something on the false branch of our if statement as well. And that's easy for us to do. The way we do that is we include something called an else clause in our if statement. And if the Boolean expression evaluates to true, we execute the code in the if clause and move on. But if the Boolean expression evaluates to false, we take the false branch and execute the code in the else clause and then move on to the rest of our program. Let's go back to our code and see how the else clause works. I'll add an else clause to my if statement. And I'll just copy this line of code. And I'll say you don't have the shiny thing. So the way this will work is if this Boolean expression evaluates to true, I'll do this, and I'll come all the way down here. I won't execute the else clause. If this Boolean expression evaluates to false, then I will come down to my else clause and execute all the code between the open curly brace and the closed curly brace for the else clause. So let's see how this works. I can answer 1, and I have the shiny thing. I can answer 2, and I don't have the shiny thing. Unfortunately, I could also answer 3, and it says you don't have the shiny thing. And while that is strictly true, because I didn't answer yes, that I wanted to pick up the shiny thing, I'd really like to actually tell the user that they provided an invalid input, not just act like they entered a valid input and they didn't pick up the shiny thing. What that means is, what I'd really like is one more else clause that's a catch-all that says, well, if the first 2 aren't true, then do this and print an error message. That means, though, that I have to change this else clause because I can only have 0 or 1 else clauses in my if statement. So I'm going to change this to an else if. And as you can see, IntelliSense is helping me. I'll say, sure, that's a great suggestion. So at this point, the way this will work is if the user enters 1, it will print this. If the user enters 2, it will print this. And at this point, if the user enters 3s, it won't print anything because we haven't added to that else clause yet. Let's test our code to make sure that it works that way. 1, I have the shiny thing. 2, I don't have the shiny thing. And 3, it doesn't say anything. And of course, I want to actually say something. So I'll add my else clause. And I'll console write line something. And I'll be very courteous to the user. I'll say invalid input dork. And I need a semicolon. So now 1 still works fine. 2 still works fine. But if they give me an invalid input, I give them the invalid input message. So as you can see, there are lots of combinations of the if, else if, and else clauses that we can include in our if statement. But here's the rule. We have to have an if clause. We don't have an if statement if we don't have an if clause. So we have to have an if clause. We can have 0 or 1 else clauses. So the first example where we just did this, we had 0 else clauses. And then when I had this as my else clause, we had 1 else clause. But we can only have 0 or 1. We can't have multiple else clauses. We can have 0 up to however many we want else if clauses. So I can put more than one else if clause here. I can stack as many else if clauses in the middle as I want. And as we saw before I added this final else clause, we can just have one if clause and one else if clause, or an if clause and two else if clauses, or one if clause and two else ifs and one else. And there you have it. That's how we implement the selection control structure in C# using the if statement. To recap, in this lecture you saw how we could use a number of different variants of the if statement to implement the selection control structure in our C# code. Last time, we learned how we can use the if statement to implement the selection control structure so we can make decisions in our C# code. This time we'll look at another C# statement, the switch statement, that also lets us implement the selection control structure. Let's go take a look. Because the switch statement is another way to implement the selection control structure in C#, I've actually left our if statement code from the previous lecture here commented out so you can see the parallels between the switch statement and the if statement. The way we implement the switch statement is we provide the switch keyword, and then between parentheses we put the name of the variable we want to switch on. And the IntelliSense has suggested a great suggestion here. So the switch will work based on the value of the answer variable, which is just what we want. We used the value of the answer variable in our if statement, so it makes sense for us to use that same variable in our switch statement. We put open and close curly braces to delimit the switch statement. And as IntelliSense has already hinted, the way we actually include alternatives in our switch statement is we provide cases. I'm not going to provide a case 0. I'm going to provide a case 1. And then I include what I want to do if the value of the answer variable is 1. And that's what we did here in our if clause. So I'll just copy this up here. And at the end of each case, I need to put break. And you can think of this as the close curly brace for this particular clause or case if you want. But basically what it says is I'm all done, jump down past the end of the switch statement. Just like when we finish a particular clause in our if statement, we go past the very end of the if statement. And this looks like the very first thing we did where we had an if statement with only an if clause. So we can control F5 and we can see that we get the message if they say 1, but we don't get the message if they say 2 or 3. The next thing we did in the previous lecture is we provided the else clause so that we could print a message no matter what the user had entered as long as it wasn't 1. The corresponding piece in a switch statement is called default. And as we built up our solution last time, this is what we included under default in our else clause before, and we'll break. So now 1 gives us the shiny thing, 2 gives us you don't have the shiny thing. However, we still aren't printing a dork message if they give us a dork input, and we decided in the previous lecture that we didn't like that. So I'm going to change this to case 2. So this is like the else if answer equal to. And we'll still provide a default, a catch-all, that gets executed if none of the cases above it got executed. And here's our dork message. And we need to include a break. I'll run it again. So 1, we have the shiny thing. 2, we don't have the shiny thing. And the dork user input gives us the dork message. So the switch statement is just another way to implement the selection control structure in C#. In many ways, it's personal preference. We'll probably use the if statement more regularly, although I will say when we start using enumerations more, we've already seen enumerations, right? The force mode 2D data type is an enumeration, but as we use enumerations more, including enumerations that we define, we may find that we want the switch statement more, but really they're interchangeable, except that there are some limitations on the data type for the variable we include here. And full disclosure, it doesn't actually have to be a variable. It can be some sort of expression, but we'll just typically use variables here. But there are certain data types that we can switch on, but we can't switch on all data types. For example, we can't switch on a float because we don't have distinct values for the float that we can include here. So that's a data type that we can't switch on. It's far more common to switch on integers or enumerations. That's probably most of the switch statements you'll ever see. So again, it's personal preference. We'll probably use if statements more, but I did want to show you another way to implement the selection control structure in C#. To recap, in this lecture you learned how we can use the switch statement to implement the selection control structure in our C# code. In this lecture, you'll learn how to use the selection control structure to implement a timer component. And you're going to use timer components throughout your game in all kinds of places. Given that claim, what are some examples of where we might use timers? If you have a level that has a time limit, you could use a timer to determine when the level has finished. You could also use a timer to periodically spawn new game objects into your scene. You could use a timer for game objects that have a limited lifespan, a death timer if you will, so you can decide when to kill off those game objects because their lifetime timer has expired. If you decide to increase the difficulty in your game periodically based on elapsed time, you can use a timer to do that, and you can probably come up with lots more examples as well, cooldown timers for weapons and all kinds of other things. Let's go take a look at how we can implement a timer component using the selection control structure. We'll start by looking at the fields of our timer class. We're going to have a field that keeps track of the total seconds that the timer should run every time we run it. We'll keep track of how many seconds have elapsed since we started the timer. So this will be like a counter of seconds that will go up as the timer runs, and we'll know to stop the timer once elapsed seconds are greater than or equal to total seconds. We have a Boolean variable that tells us whether or not the timer is currently running, and I initialize that to false. And we have a Boolean variable or field called started that I also initialize to false, and we'll see why we need this field when we look at the finished property. Now I will regularly call both running and started flags rather than fields or variables. That's common terminology for when you have a Boolean that you're going to toggle to indicate a particular state of an object. So I'll probably call them flags, but they're really fields. And those are the fields we need in our timer class. Before we look at the properties, let's look at the methods. And we'll start with the run method. This is the method we called to actually start the timer. I didn't name this method start because, as you know, we already have a start method that we get from monobehavior. That's the method we've been using when we wanted to just do something once, and I didn't want to use the same name for a whole bunch of different reasons, so we called this run. So we call this when we run the timer. When somebody calls this method, the first thing we check using our selection control structure is whether or not total seconds is greater than 0. Because it doesn't make any sense to try to run a timer if total seconds is 0 or total seconds is negative. That doesn't make any sense. So we make sure we have a valid total seconds first. And then if we do a number of things. we set our started flag to true because we have started running the timer. We set our running flag to true because the timer is currently running. And we set elapsed seconds to 0 because since the timer has started, no time has elapsed yet, right? We just started this. We haven't incremented the seconds on the timer at all at this point. Where does that happen? That happens in the update method. So I'll scroll up to the update method. The first thing we check in the update method is if the timer is currently running. If the timer is not currently running, we don't want to do any of this stuff. So we need to make sure that the timer is running before we do this code. Again, the selection control structure. So if the timer is running, we need to increase the elapsed seconds, and we need to increase it by time.delta time. So time.delta time tells us how many seconds the previous frame took to execute. And remember, update is called once per frame, so each frame will be increasing the elapsed seconds value by how much time the previous frame took. And that way our elapsed seconds will just keep growing based on the time of the previous frame. And we use time.delta time because even if we have variance in our frame rate, if sometimes we're a little faster and sometimes we're a little slower, this will still all work just right. This plus equal is the same as saying elapsed seconds equal elapsed seconds plus time.delta time. So it's just a shortcut. It's syntactic sugar that lets us actually have cleaner syntax to say, I want to add this to elapsed seconds. So great, we've added time to elapsed seconds. How do we know if the timer has finished yet? We check with another if statement to see if elapsed seconds is greater than or equal to total seconds. Notice I didn't just say equal here because we're using floating point numbers, and the chances of elapsed seconds being exactly equal to total seconds is pretty slim. But if, in fact, total seconds were 3 seconds and elapsed seconds was 3.0001, that means the timer is finished. Elapsed seconds isn't equal to total seconds in that case, but it's certainly greater than total seconds in that case, so we want to stop the timer. Of course, we haven't just checked greater than because we could, in fact, exactly hit the total seconds. And we don't want to go one extra frame, we want to stop right when the timer finishes. If, in fact, the timer is finished, we say, okay, we're not running anymore. And those are the two methods in the timer class. So we can move on to the properties. Our first property is duration. This property lets us set the duration of the timer. How long is this timer going to run each time we run it? We'll look in a lot more detail about how to write our own properties when we start designing and implementing our own C# classes, but this set says that we can set the duration of the timer. We only want to allow that if the timer isn't currently running. Once you start the timer, even though on some microwaves, for example, you can just press the add 30 seconds button and it will add time to the timer, we're not going to support that here. Once you start running the timer, you can't change the duration. So we use the not logical operator to say if it's not running, we'll set total seconds equal to value. And how do we get value when we access a property? I'm going to jump over to timer test for a moment and then come back. So in timer test, here's how we access a property. At this point, I'm holding a timer object, and we'll see how we get to that in a moment. And I say dot duration. We've accessed properties before to read them, but to set them, we just use assignment and we provide the value we want to set it to. In this particular case, 3. So when we execute this line of code, we come over here and value is 3 for this example. So total seconds gets set to 3 when we execute that line of code from timer test. Our next property tells whether the timer has finished running or not. So we can retrieve this property. We don't assign to it. That doesn't make any sense. We shouldn't have a timer that we can say you're finished or you're not, independent of whether the timer is running or anything. So we can only read this property. We can only get its value. And here's why we need the started flag. If I just said not running, then we could create a new timer object and check to see if it's finished, and it would say, yes, I'm finished. I never ran, but I'm finished. That's like finishing a marathon without ever starting a marathon. You can't do it. You have to actually start and then finish. So we can't just use not running here, because when we create the timer, it's not running, and this would return true. So we need this started flag also, so we can say the timer is finished if we started it and it's no longer running. And that's why we have this Boolean expression this way. And by the way, this is the first time we've seen a Boolean expression that we were not using as a condition in an if statement, but Boolean expressions are great. They evaluate to true or false. So we've used this Boolean expression to figure out whether this property should return true or false. Finally, the easiest property of all is the timer running. All we have to do is return the running flag, and if the timer's running, it will return true, and if the timer's not running, it will return false. Back in our timer test script, we have a test object. We're going to have a timer object. The start time field lets us provide some output in our console window so that we can see how the timer is working. In the start method, this is something we haven't seen before. So we've seen get component. We've gotten the rigid body 2D component so we could add force to it, but we already had a rigid body 2D component attached to our game object when we did that. This line of code is actually adding a timer component to the same game object that this script is attached to. So once I've executed this line of code, whatever game object we have the timer test script attached to will suddenly, at runtime, have a timer component attached to it. I could just call this without saving it in a timer object, and what I just said would still be true, but I actually want to hold on to a reference to that timer object so that I can set its duration and start it running. I also save the start time so that I can output how long the timer ran. And time.time, this is not time.delta time. This is not how much time the previous frame took to execute. This is actually what is the current time. In the update method, if the timer is finished, I calculate the elapsed time as the current time minus the start time, and then I print how long the timer ran for, and then I save a new start time because I'm about to start running the timer again, and I run the timer again. So this will just keep happening and printing this out approximately every 3 seconds as we run the code. I'll build, and then we'll go back to the editor. I've selected the main camera in the hierarchy window, and as you can see, I've added the timer test script as a component to the main camera. I'm going to run the game. And as you can see, that timer component was added as the script ran. Over in our console output, you can see that the timer is running for approximately 3 seconds every time. So as I said, we're not hitting exactly 3 seconds because we're using floating point numbers and because each frame of our game doesn't take exactly the same amount of time. So this is why we used greater than or equal to check to see if elapsed seconds was greater than or equal to the total seconds for the timer. To recap, in this lecture you learned how you can use the selection control structure to implement a timer component. And hopefully I convinced you that you'll want to use those timer components all over the place in your games. In this lecture, you'll learn how to use the selection control structure and the timer component from the previous lecture to spawn game objects into the scene from a script. And of course, we'll be spawning teddy bears into our scene, so let's go do that. The first thing I'll do is run the game so you can see it in action. And as you can see, we periodically get teddy bears spawned into our game, and they bounce around and act like teddy bears just as we've seen before, even bouncing into each other. So let's see how we make this all work. I've selected our main camera, and over here in the inspector you can see I have a teddy bear spawner script attached to the main camera, and I have some fields in my teddy bear spawner script that I've populated here in the inspector. I've populated a prefab teddy bear field, and I've populated sprite fields for each of our teddy bear sprites. And the way I populated those, just like when we populated physics 2D materials into colliders, I just dragged the prefab onto the prefab field, and I dragged each of the teddy bear sprites onto the teddy bear sprite fields. So we have a main camera with our teddy bear spawner script attached, and we've populated the fields. Here in the teddy bear spawner, here's our prefab teddy bear field. To make this field visible in the inspector so we can populate it in the inspector, we've provided something called an attribute here. We've put an open square bracket and the keyword serialize field and a closed square bracket. And that makes this field be visible in the inspector. If you do a search on the internet about how do you make fields visible in the inspector, you'll see lots of people saying make them public. And that works, but it violates our information hiding principle in our object-oriented paradigm. So there's no reason to break good programming practice just to make it visible in the inspector. We can mark a field with the serialized field attribute, and that also makes it visible in the inspector while still retaining good object-oriented design. Here's where we have the three sprites that we already looked at in the inspector. And then I have some spawn control fields. I have a min spawn delay and a max spawn delay because I don't want to spawn after the same interval every time. I'd like to have some randomness in the delay between each spawns in my game. I also have a spawn timer. I told you we would be using the timer component to do our spawning, and we will. I also want to make sure that I spawn within the screen. And there are a variety of different ways to do this, but I've set a border size of 100, and then I'm going to save the range of the min spawn x to the max spawn x and the min spawn y to the max spawn y. And every time I spawn, I'll make sure I'm within those constraints. Here in our start method, I calculate those min spawn and max spawns for x and y. And as we saw in the previous lecture, we can add a timer component to the main camera. The teddy bear spawner is attached to the main camera, so we can add a timer component to the main camera, set the duration for the timer. We're not setting it to 3 this time. We're setting it to some number between 1 and 2, and then we start the spawn timer running. In our update method, we check to see if the spawn timer is finished, and if it is, we spawn a bear, and we'll go look at that method in a moment. And then we change the spawn timer duration by creating a new random number between min spawn delay and max spawn delay, setting the spawn timer duration to that new random number, and then starting the spawn timer running again. In our spawn bear method, we need to do a bunch of work, lots of which we haven't seen before. So first of all, I want to generate a random location for my teddy bear. I know my location will be a vector 3, so I call a vector 3 constructor where the x component is some random number between min spawn x and max spawn x. The y component is some random number between min spawn y and max spawn y. And then the z component looks really strange here. we have the negative Z position of our main camera as our Z component. That might be really confusing to you. You should be thinking, well, this is a 2D game, so Z should be at 0. We want it to be in the XY plane. The important thing to realize is this vector 3 that we're generating is in screen coordinate. It's pixels on the screen. It's not a location or a position in the game world. It's a position on the screen. And we need this Z component so that after the next line of code executes, Z will actually end up at 0. So this line of code converts that screen location to a world location. And luckily, because there's lots of math involved in doing this, luckily the main camera has a screen to world point method we can call, and we pass in a screen point or a screen location, and it converts it to a world point or a world location, and that's what we're saving here. So this is where we're going to actually put the teddy bear in the game world. It sometimes takes a while to understand the distinction between screen coordinates and world coordinates. The ideas are pretty straightforward, but remembering when to use which takes a little practice. I will say, I could have generated a world location and just generated it in world coordinates right off the bat, but I wanted to talk about the distinction between screen coordinates and world coordinates here. The next thing we're going to do is we're actually going to instantiate a game object. We're going to add a game object to the scene. And when we talked about prefabs, I said one of the great things about prefabs is that we can create new instances of those prefabs on the fly at runtime from a script. That's what we're doing right here. We're creating a new instance of that prefab. We're saying it's a game object. That's why I have as game object. And we're saving it into a game object variable called teddy bear. You'll discover that there are a number of different ways that we can instantiate game objects into our scene, and this is the first way I'm showing you, but I'll show you a number of other ways as we go through the courses. Now I have a teddy bear, but at this point the teddy bear is located in the world where the prefab was located in the world when we created the prefab. So now we need to move that teddy bear game object we just instantiated into the game world to the world location that we generated up here. So we take that game object and we access its transform dot position and we set it to world location. So we just moved that new game object to a different place. Finally, the game actually generates teddy bears with 3 different sprites. So we need to randomly pick which sprite to apply to the teddy bear we just instantiated. That's what this code does. So I will get the sprite renderer component for the teddy bear object. Up until this point, you've seen me calling get component on the same game object that this script is attached to, but I can get the component of a different game object as well, as long as I have a reference to that different game object. And I do in this case. I have that teddy bear that I saved right here. So I get its sprite renderer and I save it into a sprite renderer variable, just as we saved a rigid body 2D into a rigid body 2D variable when we got that component. The next thing I'm going to do is generate a random number to pick which sprite I should have this teddy bear use. When I call random.range with integers, the lower bound is inclusive and the upper bound is exclusive. So this call to random.range will generate a number that's either 0, 1, or 2. 3 is not included as a possible return value from calling random.range with 0 and 3. Now sprite number holds a number that's 0, 1, or 2. If sprite number is 0, I'll set the sprite that the sprite renderer uses to teddy bear sprite 0. Else, if sprite number is 1, I'll set it to teddy bear sprite 1. And I could say else if sprite number equal 2 here, but I don't have to. I know it has to be 2. If it wasn't 0 and it wasn't 1, then it must be 2. So I set the sprite to teddy bear sprite 2. So here in the teddy bear spawner script, we have the selection control structure here so that we can pick a random sprite for the teddy bear. And we have the selection control structure here so that we know when to spawn a new teddy bear. I did want to point out one more thing over here in the Unity editor. Watch what happens when I run my game. So I have a green teddy bear and a magenta teddy bear, but then I got another magenta one and then another green one and finally a yellow one. And sometimes, because of the way random numbers work, we could have ended up with 15 green teddy bears before we got any other color, just because that's how random numbers work. The probability is small, but it can happen, just like you can flip a coin 10 times and get heads every single time. Game developers in general often fake randomness. So we make things look random, even if they're not purely random mathematically, because if we actually go with pure randomness, sometimes it looks wrong. And our game development is all about giving the player a good, rewarding experience, not the purity of the underlying math we use for our game development. So we will actually go through some gyrations to make sure that things look random, even if they're not purely random. To recap, in this lecture, you learned how to use the selection control structure and the timer component from the previous lecture to add a spawner to a game. In this lecture, you'll learn how to use the selection control structure and something called tags in Unity to do tag-specific processing on the game objects in the scene. And of course, we will be destroying teddy bears based on the tags on those teddy bears. Let's go do that now. This is our starting project for this lecture. And this is basically the spawning teddies project, except I've made a couple of changes. Let's see a few teddy bears get spawned first. I've actually changed the teddy bear spawner script. So now, instead of having a generic prefab teddy bear and then 3 sprites that I randomly pick between, I'm actually randomly picking between 3 different teddy bear prefabs. And if I come over here to the prefabs, you can see there they are right there. I've also added an explosion to my project because we're going to be destroying teddy bears, and I didn't just want to make them disappear, I want to blow them up, so that's what we're going to do. Let's go to the teddy bear spawner script and see how using prefabs differs from using sprites. As you can see, my serialized fields are now game objects for each of those 3 different prefabs. And spawning a bear is different because I'm not instantiating a teddy bear and then getting the sprite renderer and randomly setting the sprite. I have a teddy bear game object and I'm using a different version of the instantiate method here. This is a generic. We can tell that because we have the less than and greater than sign, and I say I want to instantiate a game object and I give it a prefab. The game object I want to clone when I instantiate this. I give it the world location that I generated above, and I give it quaternion.identity, which means don't rotate it. So this is another version of the instantiate method. As I told you, I'd show you. So there aren't significant changes here, but I am doing it slightly differently. But what I'd really like to do is I'd like to destroy teddy bears, and I want to blow them up. The way we're going to do that is we're going to use something in Unity called tags. So let me pick the purple teddy bear prefab, and over here in the inspector, you can see here that this prefab does not have a tag attached to it. And I'd like a tag attached to it, so I'm going to select this drop down. And these are the built-in tags that we get for free, but none of them say, this teddy bear is filled with C4. So I'm going to need to add a tag that says, this teddy bear is filled with C4. So I clicked Add Tag, and here's our list of custom tags that we've added. And I'll hit plus to add a new tag, and I'll add C4 teddy bear as my tag. And I'll save it. Now it turns out that now I have a new custom tag in my list of tags, but my purple teddy bear still isn't tagged. So I have to come back to that prefab, and now my C4 teddy bear tag appears at the bottom of the list, so I can tag my purple teddy bear with that tag. The next thing I need to do is I need to add a destroyer script. And this destroyer script, not the destroyer of worlds, just the destroyer of teddy bears, I need to add this destroyer script to the main camera. So every second, it will go find a C4 teddy bear using its tag and destroy that teddy bear. By the way, this hierarchy window now looks strange, right? Where's the main camera and so on? That's because we selected a prefab. To get back to our normal view in the hierarchy window, just click that left arrow, and now we're back to the normal place. So I'm going to create a new script called destroyer. And before I forget, I'm going to attach the destroyer to the main camera and save my scene. And I'll open the destroyer script. This is our standard beginning script. So I'll say destroys a C4 teddy bear every second, because that's what we're going to do here. I'm going to need a few fields. First, I need to have a prefab for the explosion that I will instantiate when it's time to destroy the teddy bear. I'm going to want to populate this in the editor. There are other ways to actually find game objects and prefabs and so on without populating them in the editor, but we'll get to that later, not later this lecture, later in the courses. So for now, let's just populate the explosion prefab in the editor. We know that I want to add the serialize field attribute, and prefabs are game objects. And I'll call this prefab explosion. I also know that if I want to destroy a teddy bear every second, then I'm going to need a timer so I can know when it's time to destroy a teddy bear. So we'll use our timer component, and I'll call it the destroy timer. We'll do our standard stuff with timers in the start method. So set up destroy timer, and I'll set the destroy timer equal to adding a component. Look at how that IntelliSense is helping us there. I'll add a timer component. I'll set the duration for every second, and I'll start it running. This code that we've added has nothing to do with tagging, but we'll get there soon. And in fact, we'll get there now in our update method. So destroy teddy bear as appropriate. So when is it appropriate to destroy a teddy bear? When the destroy timer has finished. So if destroy timer finished, the first thing we'll want to do is we'll want to start that destroy timer again. That way, in another second, we'll destroy another C4 teddy bear. Find and blow up teddy bear. So, I said that we're going to use tags to help us solve this problem, but we don't know how to find a game object by its tag. So we need to go read the Unity scripting reference to figure that out. Remember, back in the editor, we can say help, scripting reference. And rather than make you guess where to find this, I'll tell you I know it's in game object, and we'll scroll down to the static methods. And the static method we want is find with tag. So this will return one active game object tagged tag. Let's open up the documentation. As we can see, it returns a game object, and we need to provide a string with the tag to search for, and it returns one active game object with that tag, and this is really important, it returns null if no game object is found. And we'll need to be careful not to try to process the game object that gets returned by this method until we've made sure that the method didn't return null. Okay, so it will give us a game object, and we have to pass in a tag. We know we get a game object back. We'll call it teddy bear. Because this is a static method we're calling, we provide the class name dot find with tag, and we give it a tag. And it's important that you remember exactly the tag we're looking for. This is case sensitive and everything. So I remember that it was C4 teddy bear. And we'll check to make sure teddy bear isn't null, which is standard practice. That's why IntelliSense helps us with that. We are in fact going to destroy the teddy bear, so I'll take that suggestion as well. But that wouldn't give us an explosion. We want to have the explosion as well. So before I destroy the teddy bear, I'll instantiate a game object. But it's not going to be the teddy bear. I'm going to instantiate the explosion. And where do I want the explosion to appear? I want it to appear where the teddy bear is. So at teddy bear dot transform dot position, and with no rotation, even though that wouldn't really have any difference visually if we rotated the explosion. This is why we want to make sure we didn't get null here, because if we try to access transform position on a null game object, we'll get what's called an exception thrown. We'll get an error in our code. So we want to avoid errors in our code, so that's why we check for null first. Okay, that's all the code we need to destroy a C4 teddy bear every second if such a teddy bear is currently active in the scene. We're not quite done in the editor yet though, because I know I want to populate prefab explosion here in the editor. But if you look down here in the inspector, there's nothing for me to populate. So what's going wrong? An important thing that I did not do over here in the destroyer script is I didn't save the script. And the Unity editor will only use the last saved version of any script you write. This is a really common mistake. You make some changes, you go back to the editor, you don't see those changes, you wonder what's going on, and it's because you didn't save. We can either save by Control-S'ing, or we can build, which is never a bad idea, but either way, now I've saved the changes I made. So here in the editor, I can now populate the prefab explosion. I'll do that by dragging it over, and I'll save my scene. Let's run the game and hope we get a purple teddy bear pretty quickly. Well, that's a shame. It's yellow and yellow. Sooner or later, there's one, and we saw it explode. And there's another one that exploded. So our destroyer script is working fine, and our purple teddy bear prefab has been tagged with the C4 teddy bear tag, so it gets exploded. I also want to show you that we can add tags to game objects from our script while our game is running. So we'll go back to the teddy bear spawner script, and here's where we were spawning a random prefab, and you'll notice that I was actually saving the teddy bear each time I instantiated it, even though I wasn't using that. The reason I did that was because after the if statement, I can set the teddy bear dot tag equal to C4 teddy bear. Now this doesn't change the prefab. It only changes the tag on this instance of the teddy bear that we just instantiated into the scene. So if you want to make sure your prefabs are tagged, you should just do it in the editor. But if you had a ton of prefabs and it was going to be a lot of work to do that, or you just decided you wanted to add tags in the scripts instead, this way we can add a tag in the script and tag game objects at runtime. So now when we run our game, we'll be destroying green teddy bears and purple teddy bears and yellow teddy bears, depending on which game object the findWithTag method returns. Let's run the game and watch what happens. And that's very disappointing, but I forgot to save my script again. So let's go ahead and build or save, and we'll try that one more time. And of course, we're destroying our teddy bears pretty quickly because we're spawning every 1 or 2 seconds and we're running our destroy timer every second and so on. So we don't actually get a bunch of teddy bears in our scene. So there you go. We've seen how we can add tags to our list of custom tags, how we can use the editor to add a tag to a prefab, and how we can add tags to game objects from our scripts at runtime. To recap, in this lecture you learned that we can add tags to our prefabs and game objects so we can process the game objects in the scene based on their tags. What will you learn about in this lesson? You'll learn about the input manager, you'll learn how to process mouse input, you'll learn how to process keyboard input, and you'll learn how to process gamepad or joystick input. We're learning how to use the input manager, so we're using the classic input API in Unity. At the time of this recording, Unity is working on a new input system package that we could also use to process input, but to use that new system would require us to use some C# ideas like delegates and callbacks and event handling that we won't learn about until the final course in the specialization. Don't worry, using the input manager will meet all our input processing needs. This is really exciting. We're finally going to be able to have the player interact with our game by providing input to accomplish actions, and that's really what games are all about. In this lecture, you'll learn how to use the mouse position or mouse location in your games. So let's get to it. This is the Unity project we'll use as our starting point. The project assets that I've included are 4 sprites, and these sprites are actually from a game that Peak Game Studios built with a team of UCCS students to teach 4th graders about Colorado history. And I've taken those sprites and I've turned them into prefabs. So if I pick one of those prefabs, we can see that I added a box collider 2D to that particular prefab. And I of course added box collider 2Ds to the other prefabs as well. Now we want to add some behavior to these characters. And we know that one way we can add behavior to our characters is to write a script and attach that script to the game object that we want to exhibit the behavior defined in the script. So let's do that. I'm creating a scripts folder here in my assets folder. And then I'm going to create a C# script that I'm going to call character. Now before I go write the script, I'm going to attach it to all my prefabs. I'm going to show you 2 ways to do that. First, let me drag one of the prefabs into the scene. So as you can see, he's in the scene and he has focus. The way we've typically done this is we've dragged a script onto a game object in our scene. And as you can see, in the inspector for this hunter, we have the character script attached. However, the prefab doesn't have that script attached. So we modified the instance in our scene, but we did not change the underlying prefab. The way we can do that is if we come over here on the line that says prefab, we can click the overrides dropdown and select apply all. And if we do that, it applies all the changes we made to the instance of the prefab to the actual prefab, which I'll show you by selecting the prefab, and you can see the prefab now has the script. I'm going to add this script to the other prefabs in an easier way by just dragging it up and dropping it onto each of those prefabs. And now all of those prefabs, I'll pick the last one and show you, all of those prefabs have the character script attached. Now let's go implement the character script to make each of these prefabs follow the mouse around. I'll start by adding a documentation comment that just says this is a character. And although we don't need the start method right now, I'm going to leave it here because I know by the time we're done with this character, we'll actually need the start method. So rather than deleting it here and then adding it back in later, I'm just going to leave it. All our work in this lecture happens in the update method. So what we need to do on every frame of the game is we need to get the mouse position and then move the character to the world position that corresponds to that mouse position. Our question now is, how do we actually get the mouse position? And we can discover the answer to that question by reading the Unity scripting reference. Because the mouse is an input device, it shouldn't surprise you that we're going to use the input class to actually get the mouse position. And in the static properties section, we have a mouse position property that we can access. I'll click this, and we can see that the mouse position property returns a vector 3, so we'll need to save the result in a vector 3. And we can also see down here in the description that the property returns the current mouse position in pixel coordinates, which I've been calling screen coordinates, and we'll address that when we go back to the script. But now we know how to access and use this property, so let's go back to the script and use it. So we'll start by converting mouse position to world position. Because we know from the documentation that the mouse position is in screen coordinates or pixel coordinates, and if we're going to move the character somewhere, we need to move the character to a world position, not a screen position. We know that the property returns a vector 3. I'll just call my variable position. Because it's a static property in the input class, I use the name of the class, and IntelliSense helped us, so I'll just tab twice to accept that I'm getting the mouse position. We also need to adjust the Z coordinate so that when we convert from screen coordinates to world coordinates, we actually end up in the Z equal 0 plane, the XY plane. We can do that by setting position.z equal to negative camera.main transform.position z, and IntelliSense gave us exactly what we need. Now we'll convert position from screen coordinates to world coordinates. And we've done this before. We converted a vector from screen coordinates to world coordinates in the Spawning Teddies lecture by calling the camera.main.screen to world point method, and we'll pass in position. So as a reminder, the way this works is we pass in position, and this argument right now is in screen coordinates, and then this method converts that position vector into world coordinates, and we're just putting it back into the same position variable. And that works fine because we pass it in here and the method does its work, and then it gets assigned back into position. The last thing we need to do is actually move the character. We could say, get the game object I'm attached to and set transform position equal to position, and that will work fine. However, because it's so common for us to access the transform position from a script, we can actually just get rid of the game object dot part of that, and this will also work fine. So we'll go ahead and build this, and we're done in the script. And when I run my game, we'll see that the character actually follows the mouse around. Now it turns out that the character can also leave the screen, and we don't really want that to happen, but we'll fix that in the next lecture. To recap, in this lecture you learned how to retrieve and use the mouse position in your Unity games. Working for the Clampdown is the title of a song by my favorite group, so if you've never heard of The Clash, you should go check them out and then come back to this video. In this lecture, we're going to clamp the character's position so that it stays completely in the scene. And we use the term clamp when we talk about keeping a value within a range of values or within a specific set of values. Recall that last time we got it so our character would follow the mouse around the screen, but the character can leave the screen. So we want to clamp the character to stay in the screen. I've done some preliminary work, including adding 2 scripts and modifying the character script to help us do that clamping. So let's look at that preliminary work first, and then we'll actually implement the clamping. I have a screenUtils class. That's a static class that does not inherit from monobehavior. So it's pretty common to write static classes that provide utilities like the math class and the console class. We're just doing a custom static class here with some screen utilities. So anytime a consumer of the class accesses a property of screenUtils, they'll start that access by saying screenUtils dot. I've got some fields that I've saved here. These first couple of fields are to support resolution changes. When you run a game in the editor, particularly if you don't just run it in the game window, if you maximize the game window when you run, it actually changes the screen resolution. So this is just to protect against that and make sure everything still works properly. The stuff that we really care about here are the screen left, screen right, screen top, and screen bottom fields, because those will keep track of the world location of the left, right, top, and bottom sides of the screen, and we'll need that to be able to clamp our character. I've also implemented static properties so that consumers of the class can get all 4 sides of the screen without accessing our fields. Remember, these are not public because we believe in information hiding. So this is how a consumer of the class will get screen left, and we call this method to handle those resolution changes. But after we've done that, we return the screen left field. We do the same thing for screen right, screen top, and screen bottom. And we have an initialize method. The initialize method needs to get called to calculate the locations of the screen left, screen right, and screen top, and screen bottom. There's some math here that is pretty straightforward. I'm not going to spend time walking through it, but if you want to really understand how this happens, go ahead and walk through this on your own. You'll see that I'm saving the lower left and upper right corner of the screen in screen coordinates, and then using our favorite screen to world point method to convert those to world coordinates, and then just saving each boundary individually here at the end. I didn't show you in the editor, but screenUtils is not actually attached to the main camera, but the game initializer script is. And the only thing the game initializer script does is call screenUtils.initialize. You'll notice that I'm actually using the awake method here, not the start method, and the awake method gets called before the start method gets called. And when we discover we really need to care about that, we'll talk about it. We don't need to do it in this lecture, but we will talk about some scenarios where we need to use both the awake method and the start method to make sure our sequencing of processing happens properly. I've also changed the character script. The character script now has two fields, the collider half width and the collider half height. So let's talk about an example of the character leaving the screen on the left-hand side. The way we can discover that the character left the screen on the left-hand side is we can take the current transform.position.x of the character and we can subtract half the collider width, so that's collider half width here, and that will give us the world location of the left-hand side of the character. And if the left-hand side of the character is less than screen left, then we know that the character is partially outside of the screen on the left. And we want to drag them back into the screen and bang them right up against the left-hand side of the screen. And we'll see how to do that before we're done with this lecture. Remember in the previous lecture, I said I knew we needed to keep the start method, and here we are needing the start method. What we do in the start method is we get the box collider 2D that's attached to the character, and we put it into a local variable called collider. And then we take the horizontal component of the size of the collider, and I'll tell you that the horizontal component of the size of the collider is the width of the collider, and we divide by 2, so that gives us half the collider width, and we save it into that field. And we do the same for the height. This actually saves us from having to divide by 2 on every frame of the game to calculate collider half width and collider half height. So this is an efficiency thing to make it so we don't have to do those divisions all the time. We just do them once here and save the results into these two fields. Update works exactly the same way it used to work, except that I now call a new clamp in screen method. And this method will make sure we keep the character clamped in the screen. As you can see, the clamp in screen method doesn't do anything right now, but we'll now implement that method to actually implement the clamping. I know that what we're going to want to do is change components of the transform.position, either X or Y, if we need to actually move the character back into the screen. We'll start by saving the current position of the character into a local variable called position. And we need to do this because we can't actually set transform.position.x or transform.position.y directly. We can set transform.position, but we can't set the properties of transform.position. So we need to save transform.position into this local variable. And before I forget, because sometimes I forget, I know at the very end I need to set transform.position equal to position, because any changes I make to this local variable don't actually change the characteristics of the game object this script is attached to. I need to do this to actually move that game object. Let's start by clamping horizontally. As I described earlier, the way we can check if the character is partially outside the screen on the left is we say if position.x, which is the center of the character, minus collider half width, that gives us the left edge of the character. If that's less than screen utils dot screen left, then we know that the character is partially outside the screen on the left. I'll take this suggestion even though it's not exactly correct, because if we did this, then we've just centered the character on the left boundary of the screen, and we don't want to do that. We need to add collider half width to make it so the left edge of the character is up against the left edge of the screen. And if you need to use a piece of paper and a pencil to draw some pictures to see why this works this way, that's great. You should go ahead and do it. When I'm doing work like this, I regularly am sketching things out to make sure I'm getting it correct. Okay, this clamps horizontally on the left but not on the right, so we'll do an else if position.x plus collider half width is greater than screen utils screen right. If that Boolean expression is true, then we know our character is partially outside on the right. So we'll set position.x equal to screen utils dot screen right minus collider half width. And I'll take that suggestion, and that will push the character so that it's right up against the right side of the screen. Now you'll notice I used an else if here, not an if. And that's under the assumption that your character is not wider than the screen. If your character is wider than the screen, you have bigger problems here. But in general, the character will not be wider than the screen. So using an else if here is appropriate. I'm going to clamp vertically as well. So I'll just type that in and then we'll come back. Here's the code to clamp vertically. And you'll notice I started here with an if because I may need to clamp both horizontally and vertically if the character has left the screen at one of the corners. So I want to make sure clamping works properly at the corners as well. So I clamp horizontally and I clamp vertically, but I might be clamping both. The logic here is very similar to what we did for clamping horizontally. So the big idea is if our current Y position plus collider half height is greater than the top of the screen, we have to drag the character down a little bit. And if position.y minus collider half height is below the screen bottom, then we need to push the character up a little bit to be clamped against the bottom of the screen. That's all the code we need to write to do our clamping, so I'll build. As a reminder, the main camera has the game initializer script attached to it. And when I run my game, you can see the character is clamped on the top, left, right, and bottom, and it works in the corners as well. To recap, in this lecture, you learned how to clamp the character's position so it stays completely within the screen. A couple of lectures ago, we learned how to retrieve and use mouse position in our Unity games. In this lecture, we'll learn how to process mouse button input in our Unity games. To support changing characters when the player presses the left mouse button, I've added a character changer script. I've selected the main camera here to show that I've attached that character changer script to the main camera, and I've populated 4 fields in that character changer script with our 4 prefabs for our 4 different characters. So changing characters is game level logic, not character level logic. So it wouldn't make sense to put this functionality inside individual characters because that's not behavior of a character. It's behavior of the game, not a behavior of a specific character. So when we have game level functionality, we want to make sure we put it in the appropriate place. At this point, we're putting it in the script that we attach to the main camera. We know the main camera is going to be in every scene that we have in our game, so it makes sense to attach this game level logic to the main camera. We may write other game manager scripts as we move along that do much more than changing characters, but we want to make sure that we put that logic at the game level, not inside other lower level objects that really shouldn't know about other objects in the game. That's just good object-oriented design. Let's go take a look at the character changer script. These are the 4 fields that we can populate in the inspector with the prefabs for each of our characters. I also need to keep track of the current character, and I need to do that because when it's time to change to a new character, I want to put the new character where the current character currently is, so I need to be able to access the position of the current character, and I also need a reference to the current character so I can destroy it before I instantiate the new prefab. In my start method, all I do is I instantiate the first prefab in the center of the screen with no rotation. So when we go back to the editor, we'll have to remove that Hunterman character because this script will actually put a new character into the screen when the game starts running. Update is called once per frame, and this is where we'll check to see if the left mouse button is pressed, and if it is, we'll change characters. I haven't implemented that code yet, so the first thing we need to do is we need to know how can we tell if the left mouse button is pressed. And it should come as no surprise to you that we're going to go look at the Unity scripting reference to figure that out. Recall that we used the input class to get the mouse position, so it makes sense that the input class may also help us find out if the left mouse button is pressed. And of course it does, so let's go find the method we need. We won't need a property this time, we'll need a method. And we need one of these getMouseButton methods. So we have to be careful and make sure we're picking the right one. GetMouseButton returns whether the given mouse button is held down. So every frame that, let's say the left mouse button is held down, getMouseButton would return true for the left mouse button. GetMouseButton down returns true during the frame the user pressed the given mouse button. So this would only return true on one frame of the game, the very first frame in which the player pressed the mouse button. And this is the one we're going to want. Clearly we don't want getMouseButton up. We want only the first frame when the player pressed the left mouse button. So we'll click this. And as we read the documentation, we see it's a static method, so we'll call it by saying input.getMouseButtonDown. It returns a bool, which will be true during the frame the user pressed the given mouse button. And we have to provide one argument when we call this method, an integer for a specific button. And if we scroll down, we can see in this example that 0 will be the primary button. So by default, the left button is the primary button on a mouse. Users can remap which button is primary and which button is secondary, but it is standard for it to be the left mouse button. And we'll use this as the starting point for our if statement to detect when we've hit the frame that the player pressed the left mouse button. I'll say change character on left mouse button. So if input.get mouse button down, and it defaulted to 0, which is what we want, we know it's time to change the character. First, we'll save position and destroy current character. We know position is a vector 3. And we just get the current position from the current character's transform position. And now we can destroy a game object that's currently in the scene by calling the destroy method, passing in the game object we want to destroy. So at this point, we're holding the position where we want to put our new character in the position variable here, and we've destroyed the current character. Because we don't want to stack up characters on top of each other, we want to destroy the old one before we add the new one. I'm going to write the code to add the new one, and then we'll talk about it. The first thing I do is I generate a random number that will be 0, 1, 2, or 3. Remember, the upper bound is exclusive when we call random.range with integers. So I'll get a number, 0, 1, 2, or 3, and I put it into prefab number. And then I use this if statement that's very similar to what we've seen before. I check if that random number is 0, and if it is, I instantiate prefab character 0 at the position where the current character was before I destroyed it, with no rotation. And then I have else ifs to check for 1 and 2. And finally, I have an else at the bottom. Remember, I could say else if prefab number equal 3 here, but I don't need to. If it was 0, 1, or 2, I already handled those. So by the time we get down here, it must be 3. You should also notice that when I instantiate the prefab, I'm saving it into my current character field because I need that for the next time that I actually change characters. We'll go ahead and build. And remember, I said we need to remove the hunter from the scene, so we'll do that. And now when I run my game, I start with the hunter because we said in the start method of the character changer that we did just instantiate prefab 0. But if I press the left mouse button, I get a different character, which still clamps fine and everything. And as I click, I just clicked twice in a row and the character didn't appear to change. And that's because over here in our character changer script, we randomly generated the same number that we generated last time to create a character. So our code is working fine. It randomly generated a new character when I pressed the left mouse button. It just happens to be the case that it generated the same random character that we did last time, so it didn't appear to change. Our code is working fine here. If that was unacceptable to you, if you wanted to make sure that you got a different character every time you press the left mouse button, you'd want to use something we haven't learned about yet. You'd want to use a while loop that kept trying to generate a new random number until you made sure it wasn't the same as the previous random number. So of course we'd need a field for the previous character number as well. We won't bother doing that here because we don't know about while loops yet, but we could solve this problem. And this is one of those cases that I talked about where the randomness is working just fine, but it looks like the game isn't working properly. And if we really wanted to, we would fake randomness and make it not be purely random to make sure the character changed every time the player pressed the left mouse button. To recap, in this lecture we saw how we can process mouse button input in our Unity games. In this lecture, you'll learn about the Input Manager. And the Input Manager is great because it lets us map named axes to particular inputs from a mouse or a keyboard or a gamepad or whatever. The powerful idea behind this is, from within our scripts, we can then check for and process input on a particular axis by name. This is a pretty basic Unity project. I've just taken the default template project and renamed my scene to Scene 0 because we're just going to look at how we get at the Input Manager and explore it a little bit, and then we'll actually use it in the next lecture. To get to the Input Manager, we pick Edit, Project Settings, and then we pick Input Manager, and you'll notice that we have a recommendation here that says consider using the new input system package instead. And as I mentioned in the lesson introduction, we're going to defer using the new input system package because it requires you to understand some C# programming concepts that we don't have yet. So we're going to use this input system instead. I said we can map inputs to axes. At this point, it looks like there are no input axes, but if we click the arrow next to axes, we can see we actually get 30 input axes by default. Let's take a look at the horizontal one. So each axis has a name that we can use to determine whether there's input on that axis from within our scripts by using the name. Each input axis has a negative button and a positive button. So if we provide input on the negative button, then the value we get for this axis will be negative. And if we provide input on the positive button, the input we get from this axis will be positive. And we also have an alternative negative button and positive button. So this particular axis is structured so that either left or A will provide negative input, and either right or D will provide positive input on the horizontal axis. So this is a pretty standard horizontal movement input scheme. There's some other settings that we can use that I tend not to end up using. This is a keyboard or mouse button mapping, and that is certainly the most common mapping we'll use. We will use joystick axis mappings if we're responding to a thumbstick, for example, on a joystick, but we'd also use key or mouse button if we're responding to joystick buttons. And one of the great things about the input manager is I'll collapse this horizontal axis, but you'll see there's another horizontal axis down here. And this one actually is on a joystick. So we'll get input from a thumbstick, a joystick axis on a gamepad, in the x-axis, so the horizontal direction, and we can even say which joystick this particular axis maps to. The default is you get motion from all joysticks, so any joystick would be providing horizontal axis input, but of course you can set it up so you have horizontal player 1 and horizontal player 2, and different joysticks would provide those different inputs. What's so great about this is that within our script, all we have to do is find out whether we have input on the horizontal axis. And we don't care if it came from a joystick or a keyboard or the mouse or some other device. We just know we have input on the horizontal axis. So it separates the actions we're trying to accomplish, like move horizontally, from the actual device input that the player is using to try to accomplish that action. I will say that the new input system does this awesome mapping between actions and inputs to implement that same separation of actions from the actual player input, but using the input manager also lets us separate those actions from how we're actually getting input on those actions, so we'll just use the input manager. To recap, in this lecture you saw how we can use the input manager to map named input axes to particular inputs, which really lets us set up the control scheme for our game. A couple lectures ago, we learned how to process mouse button input in our games. In the previous lecture, you learned how useful the input manager is. So in this lecture, we're going to refactor our mouse button processing to use the input manager. Just as a reminder, here's how the game works at this point. We can change the character by pressing the left mouse button, recognizing that sometimes we press the left mouse button and we get the same character again because of the way random numbers work. Let's convert this code to use the input manager instead. Remember, the way that we determined that the left mouse button was down was that we used the getMouseButton method in the input class to check for the left mouse button. We want to change this code to actually use the axes in the input manager instead. Back in the editor, we should actually add another input axis for changing the character. So remember, we do Edit, Project Settings, Input Manager, And we get that suggestion that we could use the new one, but we're not going to. So we'll expand the axes. And we have 30 default input axes, but we actually need a new one. So I'll just change size to 31 instead. And then if I scroll down, the very bottom input axis is the new one that I just added. And what it does is it copies the one above it down into this one. So I'm going to change debug horizontal to say change character. I'm not going to have a negative button, but my positive button will be mouse 0. I don't want it to be a joystick axis. I want it to be a key or a mouse button. And we don't need to worry about the axis or the joy num because we're just going to determine whether or not we got input on mouse 0. Now that we have our new input axis defined, how do we actually check for input on that axis? Let's read the Unity scripting reference to find out. As usual, we'll use the input class to do our input processing. And if we scroll down to the methods, we see there's a getAxis method that returns the value of the virtual axis identified by axis name. I'll click this, and we can see that this is a static method, as the input methods tend to be. It will return a float to us, and we need to provide an argument that's the axis name. Notice that the value that we get back will be in the range from -1 to 1. So inputs on the negative button would be negative, and inputs on the positive button will be positive. We defined our axis to only have a positive input. So all we really need to check to find out that we have input on our change character axis is if the float that gets returned by this method is greater than 0. And if it is, that means we have input on our axis. Back in our code, we'll say getAxis, and we need to provide the name of our axis, and I called it change character. And remember, we're just going to check to see if the input on that axis, if the floating point number that gets returned by this method is greater than 0. And if it is, we have input on the axis, and we should do all the work we did before when we were on the first frame of the player pressing the left mouse button. I'll build. And when we run our game now, I start with our miner man, and when I press the left mouse button, you probably can tell that I'm toggling through a number of different characters. Here's what's going on. When we were calling the getMouseDown method, that method only returned true on the first frame on which the player had pressed the left mouse button. Our getAxis method is returning true on every frame that we're providing input on that axis with the left mouse button, and I can't click fast enough to keep it from detecting the left mouse button being down on more than one frame. It's just a physical limitation of the mouse device. The way we can solve this is to only change the character on the first frame that we have input on that axis, but we'll solve that problem in the following lecture. So in this lecture, we added a new input axis in the input manager, and we're processing that input axis to change the character. We just have a little more work to do to make this work the way we want it to. To recap, in this lecture you learned how to process mouse button input using the input manager, and you also discovered that we have a little more work to do before we have this working the way we want. Last time, we refactored our mouse button processing to use a named axis that we set up in the input manager, but we're not quite getting the behavior we want. The problem is we need to only process that input on the first frame on which that input is provided. That's what we'll learn how to do in this lecture. So here's how our game currently works. If I click the left mouse button, I get a number of different characters. And in fact, I can hold down the left mouse button and toggle through bunches of different characters, and that's not what we want. We just want to change the character on the first frame in which the player has pressed the left mouse button. Our modifications will be in the character changer script. The way we'll do this is we'll use a flag to keep track of whether we had input on the change character input axis on the previous frame in the game. I'll need a field to do that, and my comment will say this is for first frame input support. And I called this a flag, which should have implied to you that this will be a bool variable. We just need it to be true or false. And you may be tempted to just use a really short name here, assuming you'll remember what it meant 6 months or a year from now. But let's not. Let's give it a long name that's very descriptive. So previous change character input. And that tells us exactly what it is. Did we have previous change character input? And I'll initialize it to false because when the game starts running, we don't have any change character input provided. The rest of our work will be in the update method. The first thing we'll do is we'll make sure that if we don't have change character input, that we set that flag to false. No matter what it was before, if we don't have input on the change character axis, then that flag should be set to false. So way down here, we need to add an else clause. And you can tell that we're on the right close curly brace because the corresponding open curly brace is highlighted just like this close curly brace is. So I'll say else, and because we're a long way away from the Boolean expression we checked, I'll add a comment here that says no change character input. I know it seems strange to comment just a single line of code here, but we're a long way away from the Boolean expression, so this helps our readability to know what we're actually doing in this else clause. Previous change character input should be false here. The next thing we do is up here, because we know we don't automatically want to do this processing here. We know we have input on the change character axis, but we don't yet know if this is the first frame that we have input on that axis. So we'll check. We'll say if not previous change character input, and I'll add the close curly brace as well. And this Boolean expression might look strange to you. You might think we should say if previous change character input equal false. And that would be a valid Boolean expression that would even check this condition. But if previous change character input is in fact false, then not previous change character input is true. So this is another way to check that Boolean expression, and I personally prefer just doing it this way rather than using the equal false structure for my Boolean expression. The first thing I need to do here, I need to add a line of code that is exactly as suggested to say that I am now processing the first input frame of this change character input axis. So now I'm saying, yes, I do have previous change character input. And it's important to realize that both this assignment here and this assignment down here is really saving this information for later frames, for later calls to the update method. So when I set this to true here and change the character, as you can see down below, the next time I come into the update method, if I'm still holding the left mouse button down, even if I'm clicking it as quickly as I can, even if I have input on that input axis, previous change character input is now true, so not true is false, so I won't do any of this work inside. And I won't do any of this work inside until I have a frame where the left mouse button isn't down. And when that happens, I set that flag to false, and it will keep getting set to false until I provide input on the left mouse button again and go through this process again. So we're using previous change character input to keep track from one call to the update method to a later call on the update method, whether or not we had change character input on the previous frame. That's why we need a field for this, not a local variable here in the update method, because we have to save its value from one call to the update method to a later call. Let's go ahead and build. And back in the editor, when I run the game, you'll see each click gives me a new character, as long as the random number generator doesn't give us the same character again. But I'm holding the left mouse button down here, and you can see I only had one character change, and it won't change characters again until I release the left mouse button, and then I can press it again to get another change character. So that's how we can make sure we only process the first frame of input on a particular input axis. To recap, in this lecture you learned how we can process only the first frame of input provided on a particular named axis. And this is a really powerful idea that applies to any input device we decide to use. In the previous lecture, we finished exploring how to process mouse input in our Unity games. In this lecture, we'll learn how to process keyboard input in our Unity games, so let's go do that now. We're starting with the code we had before, and we're going to convert it from using mouse input to using keyboard input. We'll start by taking a look at the input manager. So we'll go to Edit, Project Settings, and we have the input manager already selected, and we'll look at the axes, and I'll expand the horizontal axis and show you that the negative and positive buttons are left and right, and the Alt negative and Alt positive buttons are A and D, and our default vertical axis has down and up and S and W. So the standard control scheme using both the arrow keys and the WASD keys. So in our code, all our work happens in the update method, and we're not going to convert mouse position to world position, nor are we going to convert keyboard position to world position, because there's no such thing as the keyboard position. So the way we should think about this is that we're going to move the game object that this script is attached to based on keyboard input, but we're going to move it a certain amount based on that input. So we're going to push the game object around with the arrow keys or the WASD keys instead of making it follow a particular cursor on the screen. That means I'm going to delete all this and say move game object as appropriate. I'm also going to immediately save transform position into position, because position is the local variable that I'll change based on user input. Now I know because I'm going to move the game object around based on keyboard input that I'm going to need a move amount. So I'm going to come up to the top of my class here and add movement support. And I'll make this a const, and I'll make it a float, and I'll call it move units per second. and let's just say 5. We're going to set this up so that the game object moves 5 Unity world units every second if the player is holding down a horizontal key or a vertical key. And I'll show you how it can move faster than that before we're done with this lecture. So back here in update, we should check if input get axis, and we'll check horizontal first. And this time, I'm going to check not equal to 0. So remember when we were checking the input axis for a mouse input, the mouse button, we were just checking to see if it was greater than 0 because we only had a positive input mapped to our input axis, the change character input axis. Here we have both positive and negative keys mapped to the horizontal input axis. So if we don't get a 0, we know that we have input. We don't yet know if it's positive or negative, but we know we have input on the axis. If we do, I want to change my position. So I'll say position plus equal. And now I've just realized that I need this value again. So instead of calling the getAxis method again, I'm going to create a local variable here that I'll call horizontal input. And I'll set it equal to this. And now I'll check if horizontal input is not equal to 0. And now I can come down here and use horizontal input here. Because I have a horizontal input, I want to change position.x. And I'll start by taking horizontal input. We're going to be treating horizontal input as a sign. So if the negative key is pressed, the value of horizontal input will be -1 because we're using a keyboard. If the positive key is pressed, then the value of horizontal input will be +1. And I'll write this whole equation, and then we'll talk about why it works the way it does if I, in fact, say position.x plus equal here instead of equal. Now I want to take this horizontal input, and I'm going to take this suggestion times move units per second time dot delta time. And I'll drag this over here so we can read it more easily. So ignoring horizontal input for a moment, this is how many world units we want to move per second. And as we discovered when we were building timers, time.delta time tells us how many seconds it took the previous frame to execute. So let's say that's 0.1, which is a really slow frame rate. If it's 0.1, we're only running at 10 FPS. But this will then be 5 times 0.1, which is 0.5. So on this frame, I'll only move 0.5. And if it's 0.1 consistently, as we call update, it will take me 10 frames to move 5 units. I'll be moving 5 units per second. If in fact the frame rate varies, that's great. Sometimes I'll move a little further, sometimes I'll move a little less, but over the course of a second, I'll be pretty close to 5 world units. The reason this works great as a sign is because I am adding, but if I have negative input, then this expression will evaluate to a negative number, and I'll add a negative number, so I'll reduce x. X will be less than it was before I did this. And the same if horizontal input is a positive number, I'll actually add. So that's how we can use horizontal input as the sign for the direction we want to move. We certainly could write a more complicated if statement here that says if horizontal input is greater than 0, then we add some stuff. Else, if horizontal input is less than 0, then we subtract some stuff. But this is a cleaner way to do it. Vertical input works remarkably similarly, so I'll type that code and then we'll come back and look at it. I've added a vertical input variable to hold the results of calling getAxis on the vertical input axis. And then down here, I'm doing a very similar thing. If we have vertical input, then I change position Y based on the vertical input, move units per second, and time.delta time. Notice that this is not an else if. This is an if. And the reason this is an if is because the player may want to provide both horizontal and vertical input on the same frame. Players like to move diagonally. So we use an if here so that we can move diagonally. We can process both horizontal input and vertical input on the same frame. We build successfully, and when we run the game, you can't tell I'm using the keyboard to move up and down. Now watch what happens when I move diagonally. You may not have been able to tell watching the video, but I'm actually moving faster if I move diagonally. This is actually a famous bug in Doom. It's called the strafe 40 bug, because if you move diagonally, you can actually move at a faster speed. You're actually moving at 5 times square root of 2 on the diagonal. And that's because over the course of a second, we're moving 5 horizontally and 5 vertically. So if you imagine a right triangle with both of the legs being 5, the length of the diagonal is 5 square root of 2, because that's the Pythagorean theorem. So you can actually move faster diagonally than you can move either horizontally or vertically by themselves. And if I run the game again, you see that I move with the keyboard, but I change character by clicking the left mouse button. Let's convert the change character to use the keyboard as well. We'll go back to the input manager, and I'll collapse the horizontal and vertical input axes and come down to our change character axis. Remember, we were using mouse 0 as our positive button, but I can just change that to space instead. And if I do that, when I run my game, you can't tell I'm clicking the left mouse button and nothing is happening. But if I press the space bar, I'm actually changing the character by pressing the space bar. We certainly could, of course, have had an alt positive button as well. So we could have made it so mouse 0 changes the character and the space bar changes the character, either one. But I wanted to totally convert this to keyboard input, so that's what we've done. And the great thing about that change we just made is we didn't even have to touch the character changer script, because the character changer script just uses the named axis from the input manager. So we could change the input button for that input axis here in the editor, and we didn't even have to touch code to convert the changing character functionality from the mouse to the keyboard. To recap, in this lecture you learned how to process keyboard input in your Unity games using the input manager and named input axes. And you also saw that we didn't even need to change the script to change our action of changing the character, because we could just remap that input from mouse 0 to space in that input axis. In this lecture, you'll learn how to add gamepad or controller input support to your Unity games. And you don't need a rubberized Xbox Elite 2 controller that you can swap out the thumbsticks and D-pad and change the tension on the thumbsticks and all that cool stuff. Any gamepad will work with the things that we'll do today. So let's go get to work in our game to add that support. If I run the game, I can actually use the left thumbstick to move my character around. And I haven't done anything to change the game to support gamepad input. Why does it work that way? Because in the input manager, these are the horizontal and vertical axes that we've been using to support keyboard input. But you'll notice down here, there's another horizontal and vertical axis, and these are for joystick input. So we can have multiple input axes with the same name, and when we get that axis from within our script, it will get any input on any of the mappings with that particular axis name. So this horizontal input, you'll notice there are no buttons mapped to it because it's mapped to a joystick axis instead. Specifically, it's mapped to the x-axis. So deflecting the left thumbstick left and right is the x-axis on this joystick axis, so I can move horizontally with that thumbstick. I can get motion from all joysticks, or I can get motion from a particular joystick. I only have one joystick connected to my PC right now, so getting motion from all joysticks works just fine. And the vertical axis is input on the y-axis. So we don't actually have to do anything to get horizontal and vertical input from a gamepad working fine, as long as we have it working fine for keyboard input, because by default we get horizontal and vertical axes for joystick input as well as for keyboard input. I do want to point out that using a joystick, we get finer grained control over our movement. Instead of moving full speed all the time, I can just deflect the thumbstick a little bit, and you can see I can move more slowly rather than at full speed or not moving at all. Why does it work that way? Remember when I was talking about keyboard input, I said when we get this axis, the method will return -1 if either the negative button or the alt negative button is down. We'd get +1 if the positive button or the alt positive button was down, and we'd get 0 if none of those buttons were down. When we use a gamepad though, we don't just get -1, 0, or 1, we get a number in a range of -1 to 1. So I can get -0.2, for example, if I've only deflected the thumbstick a little bit to the left. So when I do this multiplication right here, I'm no longer just treating horizontal input as the sign, I'm treating it as a sign and a magnitude. And that gives us finer grained control over character movement. And of course the same applies for vertical input as well. At this point, I still change the character by pressing the spacebar, so we should change that. In the input manager, remember way down on the bottom, we created a change character axis that we started by having the positive button be mouse 0, and then we changed it to be the spacebar for keyboard input. And I'm going to change this one more time, and I'm going to make it joystick button 0, which is the A button on the joystick. And you can spend an inordinate amount of time messing around with the joystick buttons, figuring out which ones are which as you map to input axes. But I happen to know that joystick button 0 is the A button. So now when I run my game, I can of course move my character around, and pressing the A button, you can't see it, but I'm pressing the A button, changes my character. And there you go. We've actually made it so we support gamepad input as well, and we didn't change any code at all in our scripts. We only did some work in the input manager to do it. To recap, in this lecture we added gamepad or controller support to our Unity game, and we didn't have to touch our scripts at all. We did all our work by editing the input axes in the input manager. In this lesson, you'll learn about the last control structure we need to solve virtually any problem, the iteration control structure. From our previous work, you already know about the sequence control structure, where we execute statements in sequence one after the other, and you know about the selection control structure, which lets us make decisions about the course of action we'll take in our code. The iteration control structure, which is also commonly called looping, lets us execute statements multiple times. What specifically will you learn in this lesson? You'll learn how to implement the iteration control structure in C#. You'll learn about for loops, you'll learn about while loops, and you'll learn how to do collision-free spawning. In this lecture, we'll explore another control structure called iteration, which lots of people call looping. The big idea is we can repeat a block of code, a set of statements in our code, either a certain number of times or while some condition is true. So we have a couple of classes of problem we try to solve with iteration. If we know how many times we need to loop when we actually get to the chunk of code we want to repeat, we use either a for loop or a for each loop. We'll cover for loops in a few videos this week, and then we'll cover for each loops next week. In a few lectures, we'll actually see how we can iterate when we don't know how many times we need to iterate or loop when we get to the chunk of code for which we want to repeat those statements. Let's go see how for loops work in this lecture. The problem we're going to solve here is that we're going to print the squares from 1 to 10. And this is a great example of where a for loop will be really useful because we want to repetitively do something a certain number of times. So we use the for keyword, and then we have an open parenthesis, and we do three separate things in between these parentheses. We initialize what I'll call a loop control variable because it's a variable that controls the loop, and I'll call my loop control variable I. That's pretty common for loops, and I'll initialize it to a particular value. You'll notice that the IntelliSense is suggesting that I initialize it to 0, but I actually want to initialize it to 1 instead because I'm going to print the squares from 1 to 10. If I were printing the squares from 0 to 10, initializing I to 0 would have been a better choice. Then I put a semicolon and I put what's called the condition. And again, the IntelliSense is suggesting something that I don't want to use. I want to use I less than or equal to 10. And you should look at that and say that's a Boolean expression like we used in if statements because it's a Boolean expression like we used in if statements. Finally, I'll add a modifier that specifies how I'll change I each time through the loop, and this time I'll take the suggestion that I want to increment I. I then put the body of the loop in between an open curly brace and a closed curly brace, but I'm not going to do what the suggestion is, so I'll just hit delete to get rid of that suggestion. I'll finish out the loop body, and then we'll talk about how the code works after I run it the first time. So we want to console.writeLine, but we don't want to write line I. We want to write line I times I, which squares I. I'll run the code and then we'll talk about how it works. So as you can see, this prints out the squares of the numbers 1 through 10. Okay, here's how the for loop actually works. When we get to the for loop, we initialize our loop control variable, and we're setting I to 1, and then we check our condition, and 1 is less than or equal to 10, so we'll go into the loop body and execute the code in the loop body. Right here, I is 1, so we print out 1 times 1, and then we reach the end of the loop body, so we come back up here and we increment I. So we modify I by incrementing it, and now I is 2, and we check our condition again. And 2 is less than or equal to 10, so we come into the loop body again, and this time we print out 2 times 2, and we come back and we make I 3 and so on. And we just keep iterating, we keep executing the body of the loop until we print out 10 times 10, and then we come back up here and we increment I, so I is now 11, and 11 is not less than or equal to 10, so we stop executing the loop body and we go past that closed curly brace for the for loop. We come down here, which happens to be the end of our main method. So that's how the for loop works. Remember, I was very careful with my phrasing in the introduction though. I said we can use a for loop if we know how many times we need to iterate when we get to the code. So we can actually ask the user how many squares they want to be printed out. So I'll use the console write to prompt the user. And since there's a specific range that I want them to provide, I'll say 1 to 10, giving them a hint for what valid input will be, even though they can ignore that hint, and we'll see that before we're done. And then I'll declare n equal to int.parse console.readline. And as you can see, I got some nice suggestions there, so I could just hit tab to complete my code. Now I'll come down here and I'll print the squares from 1 to n instead of from 1 to 10. And I'll replace this 10 by n, so this doesn't have to be a hard-coded value. It can be the value of a variable or even an expression. And now when I run my code, I can still print the squares from 1 to 10 by entering 10. I can print the squares from 1 to 3. And I said I can ignore what the prompt says is a valid range, so I can actually say 0, and it doesn't print anything. So it's possible that the body of our for loop won't execute at all, because when I entered 0, I initialized I to 1, and then I checked is 1 less than or equal to 0. And because that Boolean expression evaluates to false, I never execute the body of the loop. I just go right past it. One more thing before we stop. I did say we can have an expression here, so I could say n times 2. And if I say I want to print out the squares from 1 to 10, I can actually print out the squares from 1 to 20 because I included an expression here in my Boolean expression. I'll change that back to n so it does what the comment said it would do. Testing one more time to make sure I didn't break anything. And that's how we can use a for loop in our C# code. To recap, in this lecture you saw how we can repeat a set of statements a number of times using a for loop. Last time, we saw how we can use a for loop to execute a block or chunk of code a set number of times. This time, we'll look at nested for loops. So what are nested for loops? Nested for loops are when we put one for loop inside another for loop. What are they good for? They're most commonly used to process 2 or higher dimensions of data, though we'll see some other examples as well in the lectures in this lesson. Let's go take a look. The problem we're going to solve here is we're going to print out the multiplication table from 1 to 10. The first thing I want to do is print a table header, and I'll start using console write, not WriteLine, to print 5 spaces. And it will become clear as we work through this problem why I'm doing that. But now I can print the rest of the table header, which will be the numbers from 1 to 10. And of course I can use a for loop to do that. And I'm going to start I at 1 here, not 0. And I'll say I less than or equal to 10, and I'll increment I each time. And now I want to print, again using write, not WriteLine, I'm going to want to print I, but I actually want to put it in a field that's 5 spaces wide, including the I, so that my table looks nice. And the way I do that is I use something called a format string. The way the format string works is I put the format string between these double quotes, and then I say what I want to print out. My format string has curly braces on both sides. The first thing I put is which of the arguments following the format string do I want to print here, and I want to print the 0th argument. I only want to print this I. But the other piece that I can provide, and there's lots more, you can read about this in the book if you want to, but just to set the field width, I can say I want this in a field of 5. So it's going to print I in a field width of 5, including the value of I. When I'm done, because I'm just printing that row, I want to do a write line. Let's run the code and see the table header. And there you go. So I have those 5 spaces at the beginning, and then I have 1 printed in a field of 5, and it's right justified. And by the way, if I made this -5 instead, then all those numbers are left justified instead, but I want them to be right justified. So I've used a regular for loop, right? There's no nested for loop here. This is a regular for loop to print the table header. Now I want to print the multiplication table. And here's where we'll get to use nested for loops. I'll start. And notice that this time, since I used I equal 1 in the previous for loop, it suggests I do I equal 1 here also, and I will. And I'll accept the rest of that too, because I want to do it the way I did above. I'm going to add spaces even though they weren't suggested there, and they're not necessary. Spaces are just what are called white space, and they're just improve readability. So now I'm going to print all the rows in the actual table. The first thing that should appear in each row is the I for that row, and I can right justify that as well. So I'll actually just grab this code right here, and that will print out I at the beginning of the row. I also know that at the end of each row, I'm going to want to have a console write line. So let's actually see what this looks like when I run it. Okay, and that's the basic stuff for my multiplication table. All I need to add is the actual multiplication table. And here's where we get to use nested for loops. Before we do, I want to point out that this I is not the same as this I. The scope of this I, the places where this I here is visible, is right there. So if I actually tried to output I down here, I'll get a compilation error. It says the name I does not exist in the current context because this is the scope of I. So I is not visible outside that for loop. And that means that this I is a totally different I from this I, even though they have the same name. You might say, well, that's confusing. You should use a different loop control variable name down here. And you could. We've been using I, but you could call it Bob or Mary. But it's pretty common to use I as our loop control variable. So it's not really confusing to most people who are used to dealing with for loops. I will say, though, that here we want another for loop, but you'll notice I get a suggestion that we use J here instead of I. And we're going to take that suggestion. That's a great suggestion, so we'll do it. And I like the rest of that suggestion too, so I'll just take it. If we use I here, that's going to be a problem because the scope of this I is here. So if I try to use I here, the compiler will say you already have an I that's in scope here, so you can't use the same variable name twice. It's also really common to use J as our loop control variable for a loop that's nested inside a loop that uses I. So now we'll actually just print out the multiplication table part of this particular row. We're only working on one row right here. So I'll console and I'll use right. And here, I'm going to again use a format string to output in a field of 5. And now I need to output the product of I times j. And we'll talk about how this works in just a moment. I think I'll get rid of this extra white space. I'm just printing each row here so I don't need to separate those chunks of code. Let's look at the output and then talk about how it works. And there you go. That's the multiplication table. You can convince yourself that this is a correct multiplication table, but it certainly is correct. So how does this all work? When we get to this for loop, we set I to 1. We make sure that I is less than or equal to 10, and it is. So we come down into the first row and we print 1. Now we get to this for loop, and j gets set to 1, and 1 is less than or equal to 10. So we print 1 times 1. And we come back to the top of this inner for loop. We make j 2. 2 is less than or equal to 10. So we print 1. We haven't changed I yet, but we have changed j to 2. So we print 1 times 2. We come back again, set j to 3. 3 is less than or equal to 10. We print 1 times 3. And we do that until this for loop is done. In other words, once we increment j to 11, 11 isn't less than or equal to 10. So we're done with this for loop. We do our right line so that we move to the next row, and that's the end of the body for our outer for loop. So we come up here and change I to 2. 2 is less than or equal to 10. So we print 2 at the beginning of our row. And now we get to this inner for loop. And this inner for loop has no memory that it ever ran before. So when we get here, we just start it fresh, like it's never been executed before. So we set j to 1. 1 is less than or equal to 10. So we print out 2 times 1, which is 2. And then we set j to 2. 2 is less than or equal to 10, so we print 2 times 2, and so on. So that's the part that sometimes confuses people with nested for loops, that when we get here, it's brand new. It's not continuing from the last time we ran this nested for loop. This is sort of getting to it for the very first time from the perspective of this for loop. You can think of this as wheels within wheels, if you'd like. So we have this outer wheel that we start, and then we spin this inner wheel, and when we're done, we forward this outer wheel 1 tick of a revolution, and then we spin this inner wheel again, and then we just keep doing that. So that's how we can use nested for loops in C#. To recap, in this lecture we saw how to use nested for loops to solve a problem. In the previous couple of lessons, we've looked at for loops and nested for loops. And with for loops, when we get to the loop as we're executing our code, we know how many times the loop will iterate. This time we'll look at while loops, which are loops we use when we don't know how many times we're going to iterate when we get to the loop. Let's go see how while loops work in C#. Our starting code doesn't have any while loops at all. All I do is prompt for and get a health value between 0 and 100, and then I print out that health value. If I run this code, you can see I can enter 0 and it's fine. I can enter 100 and it's fine. The problem with this code is that I can enter an invalid value as well. I could say I'm very healthy, I have 110 health, and it still accepts that and moves on in the code. And there are lots of times when we're going to have the player enter some information for us and we want to validate it. Of course, we're not going to have the player enter their health, right? The game will keep track of the player's health for them, but this is a good example of a value that is supposed to be within a particular range. So what we want to do now is we want to use a while loop to do something called input validation. which means validate the input. Make sure it's valid before we move on through the rest of our program. We'll use a while loop to do that. And the way this works is we'll put a Boolean expression here between the open and closed parentheses. And if that Boolean expression is true, we'll go into the body of the while loop and execute whatever code is here. And then we'll come back and check that Boolean expression again. And for as long as, or while, that Boolean expression is true, we'll keep executing the body of the loop. And the only way we'll get past the loop is when the Boolean expression evaluates to false. So what we need to do here is we need to write a Boolean expression for when the input from the user is invalid. And that might feel counterintuitive. You might be thinking, well, can't I just check if it's valid? But we really need to check if it's invalid here so that we can go in and get a new input from the user. So what does it mean for their input to be invalid? There are two ways that the health value is invalid. Either health is less than 0 or health is greater than 100. And that leads us to our Boolean expression. And of course, we learned about Boolean expressions back in the selection module. So we know how to write these. While health is less than 0 or health is greater than 100. And while that's true, we need to get a new input from the user to try to keep getting a valid input. I'm going to add a blank line because it will look nice to have a blank line between their input and the error message I'm about to write. And you can be as nice or as mean with your error message. I think I'll be nice and say health needs to be between 0 and 100. So I'm not mean, I'm not calling them names or anything. The next thing I need to do though is I've printed this error message to them, but now I need to get a new health input from them. I'll copy this code down here. But of course, I can't redeclare health. I already have a health value here in my main method, so I can't redeclare health. But of course, I can reuse the health variable. Variables are great. We can keep changing their values as we run our code. So now what will happen is I'll ask for their health and I'll read in a value. And then while they've given me an invalid value, I'll go down here and I'll print that blank line in an error message, and I'll get a new input from them, and then I'll come back here and I'll check and I'll see if this is still true. And if it's still true, I'll go back into the body of the loop again and keep doing that until this evaluates to false. When this evaluates to false, we know that health is between 0 and 100 inclusive, so we can go past the while loop and come down here to print out their health. Let's run the code and make sure it still works for valid input. So 0 is valid and 100 is valid. 101 is not valid. So we go into the body of the while loop. And the nice thing about while loops is they could keep giving us invalid inputs and even down on the negative side. And we're just going to keep looping until they give us a valid value. And when they finally give us a valid value, we exit the while loop and move on through the rest of our code. I will point out that we're making an assumption here that the user is actually going to enter an integer. So if we run the code and ask your health and they say, Bob is my health, our code blows up with something called an exception. We will learn before we're done with all the courses in the specialization how to handle exceptions, but we don't know how to do that yet. So we're going to just assume that they're going to enter integers. We'll make sure they enter an integer that's in a valid range before we move on, but we're only going to deal with integer input from the user. Although it's possible to write for loops that don't work properly, it's much more common for people to mess up their while loops so they don't behave the way we expect them to. One way to help with that is to remember the acronym ITM, which stands for Initialize, Test, and Modify. Let's go back to the code and see how ITM can help us write while loops that behave the way we expect them to. So let's talk about the I part of ITM. We need to make sure that health is initialized before we actually get to the while loop for this Boolean expression to have a meaningful evaluation. In this particular example, it's unreasonable to assume somebody did this, that they didn't include this code, but they did in fact declare a health variable up here, and the compiler won't even let us do it this way. We get an error message here, use of unassigned local variable health. So we do have to make sure that health is initialized before we get here. This is obviously a simple example, but we could have a more complicated method where we actually passed in health, and then the compiler wouldn't know that health wasn't initialized before we get here, so we'd get bad behavior from our while loop. The next thing we should do is talk about test. So the test part is the Boolean expression that you write for the while loop to decide whether we're going to execute the body of the while loop again or move on. So if we write our test incorrectly, let's say we got confused about the difference between and or, and we wrote this as and instead. You should think about this Boolean expression. Can this Boolean expression ever evaluate to true? This Boolean expression can only evaluate to true if you can think of a number that is both less than 0 and greater than 100. And you can't, right? It's impossible. So we're never going to go into the body of this loop, even if the user enters an invalid input. So this test is incorrect. It doesn't lead to an infinite loop, although there are ways to incorrectly write your Boolean expressions to get an infinite loop. This isn't one of them, but it does lead to bad behavior from our loop, not our intended behavior. So I'll fix the test. The last thing that we have to do is we need to make sure in the body of the while loop that we modify the variable that's used in our Boolean expression. And sometimes we'll have multiple variables included in our Boolean expression for our while loop, and we have to modify at least one of them. Let's see the importance of that. And this truly will be an infinite loop, because if I run the code now and I enter an invalid value, I'm just stuck in this infinite loop forever and ever. So what's happening here? I entered a -1, so this Boolean expression was true, and then I did these things, but health is still -1, so when I come back here again, that Boolean expression evaluates to true again. No matter what variables you're using for your Boolean expression, if you don't change any of them in the body of the while loop, if you got into the body of the while loop, you'll always be going into the body of the while loop. So that's an example of making sure that we do our modify correctly so that we don't get stuck in an infinite loop. And I'll test the code one more time. And it's working fine. So that's how we can use a while loop to do input validation in our code. To recap, in this lecture you learned how to use while loops to iterate an unknown number of times as we execute our code. You also learned about the danger of infinite loops and other while loop misbehavior, and you learned how we can use the ITM, Initialize, Test, and Modify acronym to help make sure that we implement our while loops correctly. In this lecture, you'll learn how to use a while loop to implement collision-free spawning. And this is really important. I had a friend who spawned a physics-based object on top of another physics-based object in his game, and the behavior was unexpected. Let's go see how to implement collision-free spawning with a while loop. I started with our Spawning Teddies project from the selection module, but then I added collision-free spawning to the teddy bear spawner script. So let's go take a look at the changes to that script. Here at the top of the script, I added some fields for collision-free spawn support. I've got a constant for the max spawn tries, so I'll only try to spawn 20 times as a maximum into a collision-free location, and if I can't do that in 20 times, I'll just give up on spawning this time I'm trying to spawn a bear. The reason I do that is to avoid getting caught in an infinite loop in case I have so many bears on the screen that I can't find a collision-free location to spawn into, and I don't want to get stuck in an infinite loop looking for such a place. For efficiency, I'm saving half the teddy bear collider width and half the teddy bear collider height, and we'll see how we use those when we actually go to look for a collision-free location in which to spawn. But rather than retrieving these values every time I try to spawn, I'm just going to retrieve them once here in the start method so I can use them throughout my code. The other two things I have here are a vector2 called min and a vector2 called max. And every time I'm getting ready to spawn a bear into a particular location, I'll set the x and y properties of my min and max vectors so that I can call a method that we'll look at when we get there to see if we can safely spawn a teddy bear into that location. I'm doing this here as fields so I don't keep creating new vector2 objects as I check for collisions, and then eventually those objects get garbage collected. It's better for me to just create those objects here once and keep changing the x and y properties instead of creating tons of new objects when I don't really have to. In the start method, the way I save the teddy bear collider half width and half height is I instantiate the prefab, and then I retrieve its box collider, and then I take the size of the collider and get the width of the size of the collider and divide by 2. We've seen this before when we were doing clamping. So I save the half width and half height, and then I destroy that temporary teddy bear. I don't want that to be in the game. I was just creating it so I could gather these values, and now I'll get rid of it. I didn't make any changes to the update method, but the spawn bear method has a lot of work in it. We've seen this code before. I'm just generating a random location and then converting it to a world location. But then I call this new set min and max method that I wrote. And all this does is it sets those x and y properties of the vector2s for min and max. So min is actually the upper left corner of a collision rectangle for the teddy bear that I'm thinking about spawning at this location. And max is the lower right rectangle of the collision rectangle for that teddy bear I'm thinking of spawning at this location. So this method sets those two fields based on the location I'm thinking of spawning a teddy bear into. Now I'm going to use a while loop. So I start by initializing spawn tries to 1. I'm getting ready to try my very first spawn, and then I call this method to see if that location with the given size of the teddy bear is a collision-free location. And I should have mentioned before, one of the reasons I didn't hard code the size of the box collider 2D on the teddy bear is that later on somebody could change the size of that collider, and all this code will still work fine without making any modifications. Let's go take a look at the documentation in the Unity scripting reference for the physics 2D overlap area method. The overlap area method is a static method, so we call it with the physics 2D class name followed by a dot. We'll pass in a vector2 argument for point A, a vector2 argument for point B, and the rest of these parameters will have default values, as we can tell because they have equal some value for each of these parameters. So providing arguments for these parameters is optional, and we're not going to do it. We're just going to pass in 2 points. As we can see, point A is one corner of the rectangle, And that's my min vector 2, so that's the upper left-hand corner of my collision rectangle for the teddy bear. And then point B is a diagonally opposite corner of the rectangle, and that's my max vector 2, so the bottom right corner of that rectangle. We can see that the method returns a collider 2D object, so if there is a collision, it will return the collider overlapping the area. In other words, it will return the collider of the teddy bear that I will be in collision with if I in fact spawn this new teddy bear. The thing that really helps us with our while loop is if there are no colliders in the area that I gave it, it will return null. And that really helps us as we do our while loop. So this first part of my Boolean expression checks to see if the overlap area method returned non-null. It returned a collider 2D object, which means that I'm in collision. So this part of the Boolean expression will evaluate to true in that case. The collider 2D object that was returned by the method is not null, which means that we'll be in a collision if we spawn a teddy bear at the location we picked. And spawn tries less than or equal to max spawn tries. And this is our protection against the infinite loop. So it may be the case that this is true, and if that's true and this is true, then we should try another spawn. And the way we do that is we create a new location and set those min and max vector properties again and increment our spawn tries. So our spawn try counter keeps going up, and then we come back and check again. And you should notice that by calling the set min and max method, we've actually modified min and max. And by changing spawn tries, we've modified spawn tries. So we've definitely taken care of that modify part of ITM for while loops. But it might be the case that this is true, we're still in a collision, but this is false. In other words, we've tried 20 times and we're about to try the 21st time, and we need to give up. Remember, the way AND works is that both operands need to evaluate true for this to evaluate to true. So if this evaluates to false, we're going to break out of the while loop. Similarly, if this evaluates to false, we found a collision-free location, so we break out of the while loop. When we get here to create a new bear, we actually have to make sure that the location we're about to spawn into is in fact collision free, because one of the ways we exit our while loop is we gave up. So we have to make sure that we really ought to do the spawn here by making sure the location is collision free, just to protect against the scenario in which we tried 20 times and couldn't find a collision free location. We don't want to give up and then come down here and spawn into that collision anyway. So that's what this is checking. And the rest of this stuff is just what we've done before. We finally instantiate our teddy bear and move it to the world location and set the random sprite. Back in the editor, just to show you this still works properly, you can see as we watch the game that we are spawning teddy bears into the game. You can't actually see that we avoided a collision by going into the body of the while loop once, but I promise you this makes sure that we are spawning into a collision-free location, and that's another great use of the while loop. To recap, in this lecture you learned how to use a while loop to either spawn into a collision-free location or give up after a certain number of attempts to find a collision-free location. And as a reminder, this is really important. You don't want to spawn one physics-based object onto another one in your game. In the previous videos in this lesson, you've learned about for loops, nested for loops, and while loops in C#. This time, we'll use lots of what we've learned in this lesson to solve a problem. The problem we're going to solve is, we're going to print out a box composed of asterisks with a user-specified width and a user-specified height. The constraint on this problem is that both the width and the height need to be between 3 and 20 inclusive. Let's go take a look. Our code starts by getting a valid width from the user. So the standard while loop input validation stuff, I ask for a box width and I tell the user what the appropriate range is so they can at least have some chance of providing a valid input. And then I use readline to read in that string and parse it into an int and put it into width. And then while width is less than 3 or width is greater than 20, and that's an invalid width, I print an error message and I read in a new width. I do the same thing to get valid height, and I will freely admit that the way I did this was I first wrote this chunk of code and then I copied and pasted it and changed all the widths to height. And that made me feel horribly guilty as a programmer. Copying and pasting in general is a bad thing to do. You'll see me do it throughout this lecture, but especially with large chunks of code like this, that's horrible. What I really wanted to do is write a separate method that would read in a value between a lower bound and an upper bound. But we haven't really talked much about writing our own methods yet, so I didn't want to do that here. I wanted to do it the way that you would probably do it. But you should just know, when we learn more about writing our own methods, we would absolutely write a method that does this for us. Let's actually run this code so I can show you it works. So I ask for a box width and I'll give an invalid one and I'll give another invalid one and then I'll say, okay, 3 is fine. And I'll do the same for box height just to convince you that I actually have the input validation working properly, but I don't actually print out the box that I want with the user specified width and height. So let's do that now. How do we print the box? Well, the first thing we'll do is we'll print the top row of the box. And obviously, the right thing to do here is to use a for loop because we need to do something repetitively. We need to print an asterisk a certain number of times, and the number of times we need to print that asterisk is the user specified width. So if the user said, I want a box that's 5 wide, I need to print 5 asterisks. So I'll definitely use a for loop. Unfortunately, the suggestion that I start I at 0, although we could start I at 0 and use a condition that says I less than width, it might be more intuitive to say I less than or equal to width here. And I'll certainly increment I each time. And then all I need to do with a right, not a right line, is print, not a space, even though that was suggested, is to print an asterisk character. And then when I'm done with the top row, of course I need a right line to move to the next line. I'll run the code here and I'll show you that the height actually doesn't matter here. I could say 20. And it prints the top row. And clearly I want a space between the height entry and the actual box. So I'll just put this here. Testing again. And I have the top row of my box. Here's another place where I don't really like doing this, but I'm going to do it anyway. I'll print the bottom row, which is exactly the same as the top row. And now I have the top row and the bottom row. I just don't have the middle of the box. And the middle of the box is perhaps the most interesting part because I get to use nested for loops here. First of all, we'll do this one row at a time. So how many rows do we need to print in the middle of the box? The number of rows we need to print are height minus 2. Height minus the top row minus the bottom row. So I'll actually say row And I'm thinking of this as the row number that I'm printing in the box. So I'm starting by printing row 2. I know as a programmer, if I started counting at 0, I'd be printing row 1 here, but we'll do this like normal human beings, and we'll say I'm starting to print at row 2, and that means that I need to print while row is less than or equal to height minus 1. Again, I'm doing the row number here, so I'm printing rows 2, 3, 4, 5, up to row number height minus 1. I'll certainly increment row each time. So what do I need to do for each row? The first thing I need to do is print an asterisk at the left side of the row. I also happen to know that on the right side of the row, I need to print another asterisk. And of course, after each row, I need to do a right line to move to the next row. Let's see how this works. I know it's incorrect, but it should print the top row and then print the middle rows with 2 asterisks, but the correct number of middle rows, and then the bottom row. This time height does matter, so I'll do 5 for width and 7 for height. And as you can see, I have the top row, and then I have 5 inner rows, and then I have the bottom row. So everything's working great at this point. All I need to do is add my spaces. And the place I add my spaces goes right here between the left asterisk and the right asterisk for those inner rows. I'll use another for loop because I need to do this a set number of times. And look, it even suggested that I should use column and go up to height minus 1. So this is not going to be exactly correct. The suggestion is not perfect. I think I actually want to spell out column. And height is not the right choice here. I need to do column number 2 up to column number width minus 1. And I write a space here for those inner spaces. So I control F5 and I'll do the minimum size box, so 3 by 3. So I have the top row, and then I have the single middle row with an asterisk, a space, and an asterisk, and then the bottom row. And I'll run it again with the maximum box width and height. And you can see I have a big, huge box. You can pause the video there to confirm that that's 20 by 20, but it is. And that's how we can solve this problem. As I said, this is a really interesting problem because it uses all the things we've learned in this lesson. We've got while loops for input validation, we have regular for loops, and we have nested for loops. To recap, in this lecture, you saw how we can use for loops, nested for loops, and while loops to solve a problem. What will you learn about in this lesson? You'll learn how we can use arrays to store data, specifically to store multiple values in a single variable. You'll learn why we start our array indexes at 0. You'll learn how we use lists to store data. You'll learn how iteration works with arrays and lists, and we'll look at a variety of game examples using arrays, lists, and iteration. In this lecture, you'll learn how we can efficiently store multiple values in a single variable by using something called an array. We'll cover the big ideas in this lecture, and then we'll see how we implement those big ideas in C# in the next lecture. And you should also know that arrays in C# are objects. So what can we store in an array? We can store anything, but a particular array can only store a single data type. So we can have an array that holds ints, And we can have another array that holds game objects, but we can't mix different data types like int and game objects in a single array. This is a conceptual representation of what an array looks like. So typically, we will declare an array as a variable, and I have declared this array as a variable named GPAs. Now, each of those boxes that contain 0.0 is actually a location in memory, and the separate things that are stored in those locations in memory have a specific name, and that name is elements. So we talk about the elements of the array as the contents of the array. Now, in this particular array, we have elements that are numbered 0 through 9, and we'll talk in a couple of lectures about why we start at 0, but those numbers on the left-hand side give us a way of indicating which element we want to do something with. We might want to find out its value, we might want to put a value into it, but we need a way to say within this GPAs variable of 10 elements, which element we want to do something with. The number that we use to access a particular element in the array is called an index. Those are the big ideas behind arrays, but before I end this lecture, I thought you might want to see how the array discussion goes in my classroom at UCCS.
So at this point, I can tell, I feel the energy like pouring off you guys. You guys are like, holy what a tool! No, I don't mean, okay, wait a minute. All right. No, don't look at me and think, what a tool. Think about arrays and say, what a tool. Because now I can build games. And if I'm going to have 400 teddy bears, I don't need 400 variables called teddy bear 0, teddy bear 1, teddy bear 2, teddy bear 3. I can just build an array that will hold 400 teddy bears. And I just have to declare a variable once. And then I just manipulate, yay, huzzah, and there was much rejoicing.
So there you go. Thank goodness you're taking this class online instead of in a physical classroom with me at UCCS. To recap, in this lecture we learned that arrays are a good way to store multiple values in a single variable, with the limitation that a particular array can only store a single data type. In this lecture, you'll learn how to apply those array ideas we talked about in the previous lecture in our C# code. This is our game from the Stop the Madness lecture. So when I run the game, I have a character following the mouse around, and when I left click, I change the character. In this lecture, we're going to change our character changer script. So let's go over to that script. And what we're going to do is, instead of having 4 separate fields for our prefabs, we'll have an array of prefabs instead. I'm still going to want to populate that array in the editor, so I still need to include the serialize field attribute. The way we declare an array variable is we put the data type that each element of the array will be, and then we put an open and close square bracket so the compiler understands that that's an array. And now we give it a variable name, and I'll call it prefab characters. I regularly name my array variables as plural with an S on the end because my arrays hold multiple elements. So I'll have multiple prefab characters in my prefab characters array. And I'll save my changes. And back in the editor, you can see my character changer component now has prefab characters, and I can expand them. It says it's a list, but it's actually an array. And I could change the size here to 4. And then I would have 4 elements of that array that I can populate in the usual way by dragging them over from the project window onto each of these fields. I don't like doing that because then I have information in the editor that isn't actually shown here in my source code. It's much more common for us to actually create an array object when we declare our array variable. So I'm going to do that. I'll say new game object, And right between these square brackets, I need to say how big will the array object be that I want to create. And I want to create it with 4 elements. So I'll save again. And unfortunately, I have to set it to 4 here as well. So this is a manual process. It doesn't hurt me to put the array object creation. Remember, arrays are objects. That's why I used new. So I wanted to have my source code reflect the size of the array, but that doesn't actually come over here to the editor, so I still have to change it to 4. It's personal preference that I like to include the actual size of the array over in my source code. So let's populate the array by dragging each of my prefabs onto each of the elements of the array. And because I'm not using the array yet, this just keeps working the same way it did before. When we come back to our code, I can now get rid of these 4 fields because I'm storing 4 elements in my array instead. Unfortunately, that gives me a bunch of compilation errors now, so let's start working through them. The first one is on line 25, and I can double click it to go there. And that's because prefab character 0 no longer exists. We have an array called prefab characters, but I can't just pass in the entire array to the instantiate method. I have to pass in a specific game object. So we need to access one of the elements of the array. And we do that by using square brackets, and then between the square brackets, we put the index of the element that we actually want to access. So in this case, I'll just access the 0th element of the array. Normal human beings would call that the first element in the array, but it is at index 0. So now I've fixed this compilation error because I'm passing in that 0th element of the array, which is a game object, into the instantiate method. This doesn't really look like a big win at this point. We haven't really gained anything by using an array. We're about to see where we gain a lot by using the array. So down here in the update method, when I decide it's time to change characters, here's where I'm instantiating a new character. So I'm generating a random number that's 0, 1, 2, or 3, and then I have this if statement that instantiates the appropriate character based on the random number I generated. Instead of doing it this way, I'm going to copy this code right here, and I know that I can't do this, so I can say prefab characters, and then I need to put the index of the prefab that I want to instantiate between these square brackets. I'm going to move these other 2 arguments down a line because I can just take this code and put it here. So what will happen is I'll call the instantiate method. I'll say one of the elements of prefab characters, and it will be the element at index 0 or at index 1 or at index 2 or at index 3. Once I do that, I can delete all this code. And that's a huge win for us. That makes this code much more compact, and it's still easy to read as long as you understand how arrays work. I should be able to build now, and I can. And when I come back to the editor and run the game, it works just like it did before. I can move around, I can left click to change characters, and so on. I want to show you one more thing before we end this lecture. While it's often useful to populate elements of the array from within the editor, sometimes we'd rather just do it from within the script instead of doing it from within the editor, especially if we have lots of prefabs to populate or something like that. So I'm going to change this so that we actually load these prefabs into our array as the script runs rather than doing it from within the editor. The first thing I'm going to do is over here in the assets folder, I'm going to create a new folder called resources. And it has to be spelled exactly that way, and it has to start with a capital R. Now I'm going to take my prefabs folder and I'm going to drag that into the resources folder. So now I have this folder of prefabs essentially marked as resources that I can load from scripts as I run those scripts. Back in our character changer, I no longer need to mark this array with serialized field because I'm not going to populate it in the editor. Instead, I'll populate the character array here. And I'll say character prefab array. Here's how I can do that. I've already created an array object that has 4 elements. So I can say prefab characters 0 equal, and now I want to load one of my prefabs. So I say resources dot load, and I'll say game object because I am loading a game object. I'll add my semicolon now, and I need to provide a string. I need to provide the name of the game object I want to load. These are actually called Hunter Man, Miner Man, Pioneer Woman, and Skunk Woman, but they're in the prefabs folder. And I know I'm going to run off the end of this line, so I'll bring this down. So I can say prefabs / Miner Man, like that. Now, the direction of this slash matters. If I use the Windows / like this, it turns out that I get a compilation error, and that compilation error says unrecognized escape sequence. So when we actually learn about strings, we'll learn about something called escape sequences. There are 2 ways to avoid this error. One way is to just go like this. And I will show you that that all works, and then we'll come back and look at the other way to do this. So I've now loaded all the resources for the elements of the array, and I realized that Hunter Man was my first one, not Miner Man, so I fixed that. So we're loading Hunter Man into the 0th element of the array, and Miner Man into the 1st element, and Pioneer Woman into the 2nd, and Skunk Woman into the 3rd. And when I run the game, it behaves just like it did before. So this works great, and that solves that problem. I just got 3 of those Pioneer Women in a row. The other way you can do this, if you don't like using the slash in that direction, you want to use it in this direction instead, is you can actually say, with an ampersand at the beginning, you can say, I mean this string exactly like I've typed it. So don't treat this as the start of an escape sequence, just treat this string just the way I've given it to you. And I'll actually do it that way here, but either way works just fine. Building one more time, and back in the editor, when I run the game, it still works like it did before. And that's how we can convert from using multiple fields for our character prefabs to using an array instead. And we saw that that made our code much more compact as we were randomly picking a character to change to. And we also learned how we can dynamically load resources, the prefabs in this particular example, as we run our scripts. To recap, in this lecture you learned how to implement and use arrays in C#. You learned that we need to specify the size of the array when we create the array object, and independent of arrays, you learned how to load resources from our scripts as our game runs. In this lecture, I'll show you why we start our array indexes at 0. To do that, I have to use some hideous code that I've never had to use in my entire professional game development career. So don't write code like this. I just need to use code like this to show you why we start our array indexes at 0. With that big buildup, let's go take a look. This is the hideous code we're going to look at. Although the first part isn't actually hideous, it teaches you something new about arrays. So here, I've declared an integer array called scores, and instead of saying equal new int square brackets 5, close square brackets, and then doing something to initialize the contents of the array. Instead, I'm initializing the array by putting the values for the array in between this open curly brace and this closed curly brace. Given this syntax, the compiler can figure out that I want an array object of 5 elements, so it creates a new array object of 5 elements and initializes the array with these values into those elements. So if you know ahead of time what initial values you want in your array, you can use this syntax to both create the array object and initialize the array with those element values. Now we get down to the ugly stuff, and I've got to say, I have never had to use any of this in any of the commercial games I've worked on in the past or the ones I'm working on now. I had to teach myself how to do this unsafe code just to show you why we start at 0 in this video. So don't go off and say, oh, Dr. T showed me how to do this unsafe stuff and said that's how you should do it. This is absolutely not how you should do it. I'm only doing it this way because I need to get at actual memory addresses to show you how this works. In C#, we use references and let the runtime system figure out the memory addresses that go with those references, but here I need to actually skip that step and get right at the addresses. So don't do it this way. I had to mark this code as unsafe. I had to go change the configuration of the project so it lets me use unsafe code. And I'm not even going to talk about how the code actually works. What I'm going to do is just run it. And here's the important stuff. So we have our scores array, and I've listed each element in the array. So the 0th element, scores 0, is at this memory address, and it holds 100. So you can scan down this right-hand column and see that the array was initialized properly. So let's talk about why we actually start at 0. As you can see, scores 0 starts at the memory location that has this big long number but ends in 72, and then scores 1 starts at the memory location that ends in 76, and then scores 2 starts at the memory location that ends with 80, and so on. Why does this help us explain why we start at 0? It helps us because you can see each of these go up by 4, and we know in C# that the int data type takes 4 bytes. So each element of the array takes 4 bytes. That's no surprise at all. We start indexing at 0 because we can, knowing the starting address of the array and knowing what index we want to look at and knowing the size of each element, the runtime system can do some really fast math to calculate the memory location it needs to go to. So let's do an example with index 3, so the 4th element in the array. What the runtime system does is it takes this memory address, then it adds 3 times 4, the index times the element size. So 3 times 4 is 12, 72 plus 12 is 84, and that's exactly where the scores 3 element starts in memory. So if we start indexing at 0, the runtime system can do really fast math knowing those 3 things: the starting address of the array, the index of the element we're trying to access, and the size of each element. The runtime system can do really fast math to calculate the memory address to go to. If we started indexing at 1 instead, the runtime system would always have to take the index we were trying to access, subtract 1 from it, and multiply it by the size of each element and add it to the starting address of the array. Why do an extra subtraction every time you're accessing an array element if you don't need to? We avoid that by starting indexing at 0 instead. I'm going to convert this code to use shorts instead of ints and then run the code. And as you can see here, this time the memory addresses go up by 2 instead of by 4 because shorts in C# are 2 bytes, not 4 bytes like ints are. So this works no matter what data type you have for the elements in your array. This starting at 0 and doing the base address or the starting address of the array plus the index of the element you're trying to access multiplied by the size of each element, that works no matter what data type you have in the array. And that's why we start indexing at 0 for our arrays. To recap, in this lecture you learned that we start our array indexes at 0 so we can use the index to calculate an offset from the base address or the starting address of the first element in the array. In the previous few lectures, we've been exploring how we can use arrays to efficiently store multiple data values in our code. And arrays are available in pretty much every modern programming language, and they're really useful in lots of places, including in games. They do have this limitation, though, that we have to know the size of the array when we create the array object. And while that works fine sometimes, there are other times where that's a little too limiting. For example, if we're spawning and destroying game objects as we play our game, we may not know ahead of time how big an array would have to be. The good news is there's another data type we can use called lists that can grow as we need them to, so we don't have that constraint that we have to pick the size of the list when we're writing our code. What can we store in lists? Anything, but we can only have a particular list with a single data type. So we can have a list of ints and we can have a list of game objects, but we can't have a list that stores both of those things. So this is just like arrays. We can only have one element type in our list. Where do we find the list data type in C#? It's in the system.collections.generic namespace, and so we have a using directive for that namespace when we include lists in our code. Speaking of our code, let's go take a look at adding a list to a game. Our starting project for this lecture is the project that we used when we added an array to our character changer script and dynamically load our prefabs at runtime from within the script. In this lecture, we're going to refactor the character changer script to use a list instead of an array. So here, where we declare our prefab characters variable, instead of having an array, we'll have a list. So list is the data type, and list is a generic data type, so we put the data type for the elements in the list between this less than and greater than sign. And we've used generic methods. The add component and get component methods, for example, are generic methods because we put a data type here between less than and greater than. List is a data structure that is a generic data structure where we do the same thing. Of course, I don't create a new array anymore. Instead, I create a new list of game objects. Lists are objects just like arrays are objects, so we use new to call the constructor, and we provide the data type here, and we're calling a constructor, so we need those open and close parentheses as well. You'll notice that I didn't have to specify the size of the list here. One of the most powerful things about lists is we don't have to know the size when we create the list object. Lists will automatically grow if they need to as we add more elements to the list, so we don't have to know a priori how many things we're going to put into the list. Speaking of adding elements to the list, here's where we were setting each of the elements of our array, and we don't do it that way anymore with a list. Instead of doing this, we call the add method on the list, and we pass in whatever it is we want to add to the list. So remember, this list is a list of game objects, and resources.loadGameObject returns a game object. So once we call this method to load our Hunterman prefab, we're holding the game object for a Hunterman prefab, and we can add that to the list. I'll make the other syntactic changes required to do the rest of these, and then we'll come back. Now that I've changed this code to add each of those prefab game objects to the list, we have one more thing to look at when we instantiate a new prefab. So down in our update method, here's where we're instantiating a new character, and I'm going to compile without making any changes here at all. And as you can see, the build succeeded. The way we access elements of a list is identical to the way we access elements of an array. We put the name of the list, we put an open square bracket, we put the index of the element we're trying to access, and we put the closed square bracket. So lists use the same syntax to access an element in the list as we used to access an element in an array. We're done here in the code. Let's go back to the editor. And when I run my game, it behaves just like it did before, even though I'm getting unlucky with my clicks and getting the same character a few times in a row. So that's how we can use lists to store multiple elements of a particular data type in our game. To recap, in this lecture you learned how to replace an array with a list in our code. Even though this example didn't actually grow the list, so we didn't take advantage of the full power of changing the size of the list as the game ran, it does give you the tool to be able to have such a list when you need it as you write games that do in fact spawn and destroy objects as the game plays. In this lecture, we'll learn how to add a DLL, or Dynamic Link Library, to our Visual Studio project. And I will confess that this used to be part of the for loops lecture that comes next, but it made that lecture too long. DLLs are really useful for when somebody has written code they want us to be able to use, but they don't want to give us the source code. So they can give us this DLL that we can include in our project, and then we can use that code without actually having access to the source code. Let's go see how we can do that. I've already created a Visual Studio project for my for loops lecture, and this is the project we'll add our DLL to. As you can see over here in the Solution Explorer, I've already added the console cards DLL file to my project folder at the same location as my program.cs file, but that doesn't actually make the DLL accessible to our code. What I need to do is I need to right-click on dependencies, and I'm going to add a project reference. Over here, I can browse for the project reference I want to add, and I'll navigate to where the DLL is, and then we'll come right back. So I've navigated into my for loops folder for this particular Visual Studio solution, and here's my console cards.dll file. So I'll select that and I'll say add, and as you can see, it's included in the list up here and it's checked, so I'll say OK. Now we'll go take a look at the documentation for the classes and the enumerations that are in that DLL. So this is the documentation that I generated from the documentation comments that I included in those classes and enumerations, and I used a tool called Sandcastle to actually generate this documentation. As you can see on the left, I can select console cards, and that gives us a list of the classes and enumerations that I've included in the console cards namespace. So I built this DLL off a specific namespace called console cards. If I pick suit, for example, I can see that I have 4 different possible values for this enumeration: clubs, diamonds, hearts, and spades, and the rank enumeration looks very similar. For the card class, I can see that I have a constructor that will construct a card. Although you won't explicitly use that constructor as you do your work with this namespace, the deck will actually create all the cards that are included in the deck. There are 3 properties for a card object: face up, which gets whether or not the card is face up, rank, which will get the card rank, and suit, which gets the card suit, and one method called flip over that flips the card over. Our deck class has a constructor that will construct the deck, one property that tells whether or not the deck is empty, which is useful if you're using the deck for a game and you're drawing cards from the deck. You want to know when it's empty so you don't try to draw another card. That just makes you look silly. And then the number of methods. We can cut the deck at a given location, we can print the cards in the deck, we can shuffle the deck, and we can take the top card from the deck. And the take top card method is the only method we'll use in our for loops lecture, but the deck class exposes these other methods as well. Okay, let's go back to our Visual Studio project and finish adding the DLL to our project. So let's say I wanted to include a deck object in my code. I might come down here and say I want a deck object, and we immediately discover there's no such thing as the deck class yet because the deck is included in the console cards namespace, which means we need a using directive. And we need a using directive for console cards, which is in the DLL that we just imported. Let me finish this variable declaration, and when I go to compile, we actually get an error. And the error is right here, so the assembly console cards has a higher version than what we have here. So our version here is .NET 5.0. I created the project targeting .NET 5.0 so I would get the template for the console app as we discussed when we talked about the first console app, but I actually built the DLL for .NET 6.0. So what do? This is an easy fix that I already showed you when we talked about our first console app. I can right-click the solution and select Properties, and I can change the target framework for my project to .NET 6.0 instead. And I'll save, and I'll close, and now when I build, my build succeeds. So you may come across instances where the DLL was built to a higher target framework than your current project is, and the best approach to take is to make the target framework for your project match the target framework for the DLL you've included. If you've included multiple DLLs that have multiple target frameworks, you can generally set your project to the highest framework of all those DLLs, and everything should work fine. To recap, in this lecture you learned how to add a DLL to your Visual Studio project, and this is really useful when someone has written code that they want us to be able to use, but they didn't want to provide the source code to us. Now that you know about both lists and for loops, in this lecture we'll explore how we can use those two things together. Let's go do that now. This is the Visual Studio solution that we set up in the previous lecture. So we added our console cards DLL to our project, and we have a using directive for the console cards namespace. And I should actually create a deck object here rather than just declaring the variable. So we'll call the constructor to create a new deck, and I'll add a comment above it saying create deck and hand. We'll have a hand of cards. So I'll make my hand of cards a list of cards, and I'll call it a hand, and I'll create a new card list. But I'm getting compilation errors there because it can't find list, and that's because the list class is found in System Collections Generic. So in general, when you include something like a list or a deck that you know is available somewhere and the compiler complains that it can't find it, the first thing you should check is if you're missing a using directive. Next, we'll add some cards to our hand. And I can just do that by calling the add method on the list. And the way I get the cards is by taking the top card from the deck. So it is very unusual if we're playing an actual card game for people to add cards to their hand by creating new cards with a card printer off to the side. We draw cards from the deck. That's the common way to add cards to a hand. So we can just call the deck take top card method to actually add a card to the hand. Remember, our documentation said take top card returns a card to us, and we can then just add that card to our hand list because our hand list is a list of cards. So let's do that a few times. And finally, we'll get to the for loop part. We'll print cards in hand. And here's our for loop. Let me tab and accept that. And you can see we have some other suggestions, and these are great suggestions too. So I'm going to accept all those suggestions. Let's add code to the body of the loop. And all we want to do is print out the card in the hand. So I'll console.writeLine. And I don't want to say just hand I. We'll actually run that and see what happens. But let's talk about how I works first. Then we'll run it. Then we'll fix this. The first time through the loop, I is set to 0. So the first time through the loop, this console write line will print out the first element in the list at index 0. Because that's the only thing in the body of the loop, after it's done that, we'll come back up here and we'll increment I. So I is now 1. And we'll check to see if I is less than hand.count. And it is, because hand.count is 3. We have 3 cards in our hand. And 1 is less than 3. So we'll come into the body of the loop again. And this time, I is 1. So console write line will print out hand 1. We'll loop again. Set I to 2. 2 is less than 3. We'll come into the body of the loop and console write line hand 2. And then we'll come back again and increment I. So now I is 3. And 3 is not less than 3. So we'll exit the loop. This less than might have seemed counterintuitive to you. You might have thought we should do less than or equal to make sure we get that last card in the hand. But remember, we started indexing at 0, not at 1. So the valid indexes for our hand are 0, 1, and 2. You should also note that I didn't just hard code 3 here. I actually accessed the count property of my hand list, because that way, if the size of my hand changes, I don't have to try to figure out how to change the hard-coded upper bound for this Boolean expression. I can just dynamically use the correct number based on the contents of the hand. Let me show you why I said that this part is not what we really want to do. Because when I run the code, just printing out hand, what it tells me is the actual class name. So it's the card class. Each card in the hand is a card. And it gives me the fully qualified name. So it's console cards, the namespace, dot card. That's not really what I want. What I want is the rank of the card. And I'll concatenate that with the suit of the card. So now if I run again, you see I have the king of spades, the queen of spades, and the jack of spades. And I didn't shuffle my deck so that I could confirm that I was actually getting the correct cards. Now I manually added cards to the end here one at a time by copying and pasting, but we can certainly use a for loop for that as well. So add 5 more cards to hand. I'll set I to 0. This time I'm not going to take the suggestion. I'm going to say I want I less than 5, and I will increment I each time. And I will add, and I just tabbed to take those suggestions there, to take 5 more cards and add them to the hand. And I'll print the cards in the hand again. And I think I'll add a blank line so we can see where the different prints are separated. And when I run my code, you'll see I now have 8 cards in my hand. So the for loop added the 10, 9, 8, 7, and 6 of spades to my hand. And because I used hand.count here, it printed out all the cards in the hand. I do want to point out a few things. First of all, we looked at initializing and the condition and modification. We don't have to always initialize to 0. It's most common to initialize to 0, but I could also add 5 cards to the hand by saying I is actually going to start at 1, and we'll say I is less than or equal to 5. So now instead of counting 0, 1, 2, 3, 4, we're counting 1, 2, 3, 4, 5. And I'll show you that that still works exactly the same way. And as you can see, it does. And we don't even have to modify just using an increment. I can change this. This is, of course, still an increment. But I can run that code, and it does the same thing. And I could even add, this would be a mistake, but I'll do it anyway. I'll say I equal I plus 10. And of course, you should realize if I do that, the first time through the loop, I will be 1, so I'll take 1 card. But then I'll change I to 11, so this condition will no longer be true, so I'll only actually add 1 card. This is a mistake for this particular problem, but I'm just showing you that we can have a different modifier as well. So as you can see, I only got 1 more card. I got the 10 of spades. So I'll just change this back to I++. So we've added 3 for loops to this code. This one prints out all the cards in the hand and uses hand.count in our Boolean expression. This one hard codes the upper bound in our Boolean expression and doesn't set I to 0 and doesn't use less than here in our Boolean expression. And this one prints the cards in the hand again using hand.count as our upper bound. And that's a best practice, to use hand.count as our upper bound for loops that we're using to iterate over lists.
To recap, in this lecture you learned how to use for loops with lists. In several previous lectures, we've seen how we can use for loops when we know how many times we're going to iterate when we get to the for loop in our code. In this lecture, we'll look at how we can use for loops in a slightly different way to solve a standard game development problem. So what's our problem? Our problem is that teddy bears don't live forever. And if we have a list of teddy bears that we're maintaining, we need to remove the dead teddy bears from that list. Otherwise, we'll waste time processing those dead teddy bears every time we iterate over the list. And of course, these ideas apply to all lists, not just lists of teddy bears. Let's first look at a counterexample, the way we shouldn't try to do this. So we shouldn't try to do this with a forward for loop. And that's the only kind of for loop we've written so far. Let's see why. Here's the list of teddy bears we're going to process. The 2 teddy bears in the middle, the ones with red X's on them, are dead teddy bears that we want to remove from the list. We're going to start our loop control variable, I, at 0, and our condition will be I less than the count of the elements in the list, which starts as 4 because we have 4 teddy bears in our list. Our first iteration through the loop We look at element 0, and that's a live teddy bear, so we're going to leave it alone. And we loop back to the top of the loop, and we increment I to 1, and we look at the teddy bear at element 1, and we see that that teddy bear is dead. So we remove it. One of the things we know about lists is that if we remove an element from in the middle of the list, or even at the beginning of the list, the rest of the elements shift down. And that happens when we remove the dead teddy bear that's currently at element 1. Now we go back to the top of the for loop again, and we increment I to 2, and count is now 3 because we removed a dead teddy from the list. But I, which is 2, is still less than 3, so we're going to go into the loop again. But you'll notice that the teddy bear at element or at index 2 is the live teddy bear that used to be at the end of the list. So because the elements in the list shifted down when we removed that first dead teddy bear, we skipped over the second dead teddy bear as we were processing the list. So when we're done doing this with a forward for loop, we end up with a dead teddy bear still in the list. As a reminder, this is a counterexample. This is not the way we want to do it. Here's how we should do it. Let's start with the list again, but this time we're going to work our way backwards through the list. We're not going to go forward, we're going to go backwards. So we start I, our loop control variable, at the count of the elements in the list -1. So we're at the very end of the list. And we're going to decrement, we're going to subtract 1 from I on every iteration. And we're going to keep looping as long as I is greater than or equal to 0. So we'll make sure we don't run off the left side of our indexing by checking I greater than or equal to 0. Let's see how this works. We first look at the teddy bear at index 3, and that's a live teddy bear. So we leave it alone, and we come back to the top of the loop again, and we decrement I. So I is now 2, and that is a dead teddy bear. So we remove the element 2, the dead teddy at index 2, and that shifts the end of the list down. So we now have that live teddy bear in index 2. But when we loop back around, we are going to decrement I again, and I is now 1. Count moved down to 3, but we don't care because we're going right to left, so we're checking I greater than or equal to 0. And we also don't care about the shifting of that live teddy that is still at the end of the list. It's just squished over 1 because we already processed those elements. So now I is 1. We have another dead teddy, so we remove it, and now our list looks like 2 live teddies. We still need to look at the last one, the one all the way on the left, but now our list is 2 live teddies. We've decremented I to be 0, and our count is now 2, but again, we don't care because we're not comparing to count in our condition. And finally, we look at the teddy bear at index 0, and it's a live teddy bear, and we just leave it alone. So the good news is that we've gone backwards through our list, removing dead teddies, and we made sure we removed all of them. The other clue that we have that this way worked is we iterated 4 times, which means we processed each of the 4 teddy bears that were in the original list. In the counter example, we only iterated 3 times on a list of originally 4 teddy bears, so we know we missed one. To recap, in this lecture you saw how we not only can, but should use a backwards for loop if we're planning to or might remove elements from the list as we iterate over the list. In the last few lectures, we've explored how we can use for loops to iterate over lists. In this lecture, you'll learn about for each loops, which provide us another way to iterate over arrays and lists. Our starting code for this lecture is the for loops code we had, where we created a deck in hand, added some cards to the hand, printed the cards, added some more cards, and printed the cards again. What we're going to do in this lecture is we're going to convert each of the for loops that we can convert into a for each loop into a for each loop. The first loop we can do that with is printing the cards in the hand. So instead of doing a for loop, I'm going to do a for each loop. And of course the syntax here is different as well. And the way this syntax works is the first thing we put is the data type for each element in the array or list we're iterating over. So we know hand holds a set of cards. So card is the data type of each of those elements. And if you've forgotten, you could just look up here and see what data type the hand holds. The next thing we do is we provide the name of a variable that we want to use within the body of the for each loop when we're referring to that element in the list. And I'll call this card. So this looks a lot like a variable declaration where we have a data type and a variable name because it essentially acts like a variable declaration. So anywhere between this open curly brace and this closed curly brace, we can just access card like we access variables. The next thing we put is the keyword in because we're iterating over each of the elements in a particular array or list. And finally, we put the name of the array or list we're iterating over. Of course, we have syntax errors here because we no longer have an I. Instead, we have a card variable. So I'll change this to card. And I'll change this to card. So how does this work? The first time through the loop, card is assigned the value of hand 0, the 0th element in the hand list. Then within the body of the for each loop, we reference that card variable, and then we loop back again, and card gets assigned the element at index 1 in hand. And so on. So each iteration through the loop, we're processing another element of the array or list that we're iterating over, and this automatically runs the correct number of times based on how many elements are in the array or list. Let's go ahead and run this code. And as you can see, that first printing out the cards loop works just like it did before, except this time we're using a for each loop. Anytime we use a for each loop, we could use a for loop instead, as you can see from this particular example. But the standard practice in C# is when you can use a for each loop, you should use a for each loop. Let's look at the next for loop in our code. Here, we're not actually iterating over an array or list. We're modifying a list here, but we're not doing something to process each element in an array or list. We just start this for loop at 1, and we iterate 5 times, and then we stop the for loop. So we can't convert this for loop into a for each loop because this for loop is not iterating over a list. Even though it's modifying a list, it's not iterating over a list. It's just iterating 5 times. So this is one example where we can't convert a for loop to a for each loop. This last for loop prints the cards in the hand, so I'm going to just come up here and take the loop that I used to print the cards in the hand. And I'll paste it there, and we'll test again. And that loop, of course, works properly as well. I want to show you another example of something we cannot do in for each loops. Let's say, even though we would never actually do this as we're printing out the cards in the hand, let's say after printing a card, we decided we wanted to remove that card from the hand. So we could say hand.remove, and card is the thing we're going to try to remove. I'll run the code. And as you can see, we get an exception here. We have an invalid operation exception,
and it says that the collection was modified. And I probably didn't say this when I was covering lists, but lists are actually something called a collection class. That's why it's in the system.collections.generic namespace. So the list is an example of a collection class. It's a collection of elements. That's not the point here, though, with this example. The point here is that within a for each loop, we're not allowed to modify the array or collection or list, right, that we're iterating over. So we can't do this inside a for each loop. If in fact we need to modify the array or list that we're iterating over, we have to use a for loop. We can't use a for each loop. So I'll get rid of this bad code and test it one more time, and everything still works fine. So we saw two examples of places where we can't replace a for loop with a for each loop. We couldn't replace this one because we weren't iterating over an array or list. And even though I removed the code, we couldn't use a for each loop here if we were going to modify the list. But we also saw an example here, and really the same functionality here, where we could replace a for loop with a for each loop. And just to reiterate, using a for each loop is standard practice in C# when we can use a for each loop instead of a for loop.
To recap, in this lecture you learned about for each loops, which provide us another way to iterate over arrays and lists. And we learned that for each loops are best practice for C# programmers. If you can use a for each loop, you should. But we also learned that there are some scenarios in which you have to use a for loop. You can't actually use a for each loop. I'm sure that based on the past few lectures, you're excited about the power of lists. I'm also sure that you must have one burning question. Specifically, how can we use lists to have teddy bears collect things? I'm here to help. In this lecture, we'll build a small game in which teddy bears collect stuff, and we'll use lists to implement that functionality. Let's go take a look.
Here's our Ted the Collector game, and I'll start by showing you how it works. I can place pickups, which are little Dr. T heads, by clicking the right mouse button, and then when I want the teddy bear to start collecting, I left click the teddy bear and he starts collecting, and I can add another head while he's collecting and he'll go get it. But if I add more now, I have to click the teddy bear again for him to go collect those. And he collects those pickups from oldest to newest. My main camera has a Ted the Collector script attached to it, and my teddy bear has the teddy bear script attached to it. Let's go look at the teddy bear script first. In the teddy bear, we have a number of fields. We have a constant for the impulse force magnitude that I'll use to get the teddy bear moving when I need to add a force. I have a flag that tells whether the teddy bear is currently collecting or not, and we'll see why I need that soon. I also save the target pickup, the pickup that I'm currently going toward to pick up. And then for efficiency, I save the rigid body 2D that's attached to this teddy bear object, and I save a reference to the Ted the Collector script, that script that's attached to the main camera. And I save both of these for efficiency, so I don't have to go get those components every time I need them. I just need to get them once, and then I can use them while the game plays. In my start method, I make sure that the teddy bear is centered in the screen. The vector3 class has a 0 property, which just returns a vector3 object with zeros for the x, y, and z components, and setting transform position to 0, 0, 0 centers it in the screen. Here's where I save those references. This get component works just like we've seen before, where I get the rigid body 2D that's attached to the same game object that this script is attached to, the teddy bear game object. And for the Ted the Collector script, it's attached to the main camera. So I say camera.main, and then I can just call the get component method on the main camera to get the Ted the Collector script.
OnMouseDown is a method that's called when the user has pressed the mouse button over the collider. So on top of the teddy bear, I don't just left click anywhere, I have to left click on the collider of the teddy bear. When that happens, I first make sure I'm not collecting. If I'm not collecting right now, I'll go to the next pickup. And if I am collecting right now, I'm just going to ignore this mouse click because the teddy bear's already been tasked to go collect a pickup and there's no reason to respond to more clicking on the teddy bear. OnTriggerStay2D is a method that gets called when another object is within a trigger collider attached to this object. I have one trigger collider attached to this object. The way I make a collider a trigger collider is here in the box collider 2D component that I have attached to the teddy bear. I check this checkbox that says is trigger, and that makes this a trigger collider rather than a normal physics collider. I don't want it to be a normal physics collider because I don't want it to run into the pickups and have that collision resolved with physics responses. I just want to do some processing when I have that collision. So by checking this is trigger checkbox, I'm basically saying the physics 2D engine shouldn't do any collision resolution for me other than calling one of the onTrigger methods. As you can see in the scripting reference, we get 3 onTrigger methods that get called when another object is colliding with the trigger for this game object. We get onTriggerEnter2D, which is called the very first frame in which we have an overlap with that other game object's collider and our trigger collider. And this is just like the onCollisionEnter2D method that we've seen before that we used to do collision resolution. We have onTriggerExit2D, which gets called on the first frame in which the other object leaves our trigger collider. And we have onTriggerStay2D that gets called every frame that another object is overlapping with our trigger collider. And this is the one that I'm using in my code. I started by using onTriggerEnter2D, but it turned out that it didn't work if I had 2 pickups that were very close to each other. Because what would happen is onTriggerEnter2D would get called when I collided with the target pickup, but when I went to get the next pickup, if it was really close, onTriggerEnter2D didn't get called because the colliders were already overlapping. And onTriggerEnter2D only gets called on that first frame of overlap. So by using onTriggerStay2D, I solved that problem because as soon as I destroyed that target pickup, onTriggerStay2D got called because the other pickup was already overlapping with my trigger collider. I check to make sure that the game object for the other object that just entered my trigger collider, even though I'm the one that's moving, right, the other object has entered my trigger collider. So of course I have a collider attached to my pickups as well. I check to make sure that that's the target pickup because I may pass over other pickups on my way to my target pickup, and I don't want to respond to those collisions. I only want to respond to collisions with the target pickup I'm trying to go pick up. If in fact I've just reached my target pickup, I call a method in the TED the Collector script called removePickup. So take out that pickup that I've just collected. I set my velocity to 0. And while we often modify the velocity of our rigid body 2D by adding forces to it, in this particular case, I want to directly access the velocity property and set it to 0. The reason I want to do that is each time I pick up a pickup, I want to stop, and then I want to start moving toward the other pickup. If I just kept adding forces to change where I'm going, I will make the teddy bear go faster and faster, and that's not what we want to have happen. After I do that, I go to the next pickup, which is the same method that I called here when I clicked on the teddy bear. So in the go to next pickup method, the first thing I do is I access a property in the TED the Collector script which says give me a target pickup, and I save that here in my field so that when I have a collision, I can check to see if that's the target pickup for me. And if the target pickup isn't null, it's possible, and we will look at this property soon, it's possible that this target pickup property will return null, so we need to protect against that before we do anything with the target pickup. If the target pickup object isn't null, the first thing I do is I calculate the direction from my location to the target pickup's location. And we've seen similar things to this before, where we were trying to calculate an angle to get from where a particular game object is to where another game object is in one of the very first programming assignments you did. So I take the target pickup's X location and subtract my current location, the target pickup's Y location and subtract my Y location, which gives me a direction vector. But this direction vector has a magnitude that is based on how far apart I am, the teddy bear, from the pickup. The next thing I do is I normalize that, so I make it a unit vector. I make it a vector that has a magnitude of 1, and I want to do that so that the force vector that I apply when I call the add force method on my rigid body 2D, this is a unit vector, and I multiply by that constant for how much force I want to apply. And by making sure direction is a unit vector, I will always be applying an add force with a consistent magnitude. And of course, it's an impulse force like we're used to using. And that's the end of the teddy bear script. The Ted the Collector script has a prefab pickup that we populate in the Unity editor. That's why I've marked it with the serialized field attribute, and this Ted the Collector script, which you can think of as a game manager. It does game level stuff, not behavior that really belongs in a specific teddy bear. So this Ted the Collector script also keeps a list of game object of all the pickups that are currently in the game. Here's that single property we've been talking about. So when the teddy bear script asks for a target pickup, the first thing we need to do is make sure the list of pickups isn't empty. If the list of pickups is empty, there's no target pickup to provide, so we return null, and we've seen how we handle that scenario in the teddy bear script. But if there's at least one pickup in the list of pickups in the game, we return pickups 0, which is the pickup that's at the front of the list, and that also means it's the oldest pickup in the game. Because when we add pickups to the list, which we'll take a look at soon, we add them to the end of the list. So the list is ordered by age from oldest to newest. In the update method, if the user has pressed the right mouse button, add pickup on right press, not right click, on the first frame that the player has depressed the right mouse button, we calculate the world position of mouse click, which you've seen before when we made game objects follow the mouse around and so on. We instantiate our prefab, and you'll notice I'm using an overload of the instantiate method that doesn't provide a position or a rotation. I just give it the prefab that I want to have instantiated. And then I move that prefab to the world position that I calculated up here based on where the mouse is. And I add that pickup to the list. And as I mentioned, this gets added at the end of the list. The last method in the Ted the Collector script is the remove pickup method that we saw the teddy bear script call when it has picked up its target pickup. And we do two things here. Here's another list method called remove, and we can call that on our list of pickups and give it the game object we want it to remove. Now we actually know from the way this game works that this will be the pickup at the very front of the list at index 0. So we want to remove that pickup, which is the same pickup we provided to the teddy bear script as its target pickup. We want to remove that pickup. And one of the nice things about lists is when we remove an element from a list,
It shifts all the other elements of the list so they're all right next to each other again and so on. So we don't have to do any extra processing ourselves. We just remove the front of the list and all the other elements in the list get shifted down. And then we destroy the pickup, which removes it from the game.
To recap, in this lecture we use lists to have teddy bears collect things in a small game. In this lecture, we'll selectively process game objects in our game using a list and a for loop. And the title may have already given this away. The game objects that we're going to process are teddy bears, and by process, I mean blow up. Let's go see how we can do that.
As usual, I'll start by showing you how the game works. So when I run the game, I'll be spawning teddy bears of 3 different colors. And for the green teddy bears, I can press the right mouse button and destroy it. For yellow teddy bears, I can press the left mouse button. And for purple teddy bears, I can press the middle mouse button. And I can keep blowing up teddy bears for as long as I want. Our main camera still has the teddy bear spawner script attached to it, but I've also attached a blowing up teddies script. So this is the game manager that will manage the different game objects in the scene. And I've added a prefab explosion and sprites for the 3 different teddy bears. And this reminds you that we can have multiple scripts attached to a single game object in our scene. Let's go take a look at the 2 new scripts that I've added to our game. The teddy color script is not particularly exciting. It's just an enumeration of the 3 different teddy bear colors. So I have green, purple, and yellow teddy bears in my game. And you'll see where I use this enumeration to specify the color of the teddy bears that I want to blow up. All the heavy lifting for this game is in the blowing up teddies script. We already saw the serialized fields that I have. I also have a list of game objects. I'm regularly going to retrieve a list of game objects, and rather than creating a new list every time I do that, I've just declared a field here so I can just reuse this field every time I need to retrieve that list of game objects. In the update method, I'm going to try to find all the objects in the game that are game objects. We know from the find objects of type method documentation in the scripting reference though, that that method is slow. So we only want to call that method if we actually have input on one of the input axes that we use to blow up teddy bears. I've defined 3 different input axes, one for blowing up yellow teddies, one for blowing up green teddies, and one for blowing up purple teddies. So I'm only going to go into the body of this if statement if I actually have input on at least one of those input axes. If I do, I clear my list of game objects. Because my list of game objects is probably stale at this point, I probably spawned new teddy bears and I may have destroyed some teddy bears, so I don't want to use an out-of-date list of the game objects in my game. I want to get a current list of game objects in the game, so I clear my game objects list. And then I call that method that we know from the documentation is slow, and I find all the game objects that are currently in the scene. And that method returns an array, but I'm using a list. So I'm going to now call the addRange method for the list to add each element of that array into my list. So this method is different from the add method that we've seen in the past, where we would add single elements one at a time. The addRange method actually takes in an array or a number of other data types like another list and will copy those elements from the argument that we provide to the method into this list. So at this point, we have a list of all the game objects in our game. Now we have a set of if statements that check if in fact we're trying to blow up yellow teddy bears, we're going to call a different method, and we pass in the color of the teddy bears we're trying to blow up in that list of game objects that we just retrieved above. I do the same thing for the blow up green teddies and blow up purple teddies axes, of course passing in a different color that I'm trying to blow up. You'll notice that I'm using if statements here
not else ifs or elses, because I want it to be possible for the player to actually press multiple mouse buttons or provide input on multiple of these input axes and blow up teddy bears of multiple colors all on the same frame. The blow up teddies method is going to blow up the teddy bears of the color that's provided here. You'll see that I'm using a backwards for loop. Although I'm not actually removing any items from the list as I do this processing, I do know that I'm going to actually be destroying those game objects, so even though I'm not removing them from the list, I'm conceptually removing them from the set of game objects in the game, so using a backwards for loop is a safe thing to do at this point. The next thing I do is, for the current element in the list, I get the sprite renderer component, and I put it into this variable. I have to check to see if the sprite renderer is not null, because one of the game objects that always gets returned is the main camera. And the main camera isn't a teddy bear we're trying to blow up, and the main camera doesn't have a sprite renderer component attached to it. So if I tried to process the main camera, getting the sprite renderer component would put null into this variable, and then when I came down here and tried to access the sprite property of that null object, we'd get a null reference exception thrown. And that's a bad thing, so we want to avoid that happening, and we can do that by using this if statement. Now I have a complicated Boolean expression that checks if the color we're trying to destroy is green, and the sprite attached to this game object is actually the green teddy bear sprite, that means we just found a green teddy bear and we're trying to destroy green teddy bears. Or, if we're trying to destroy purple teddy bears, and this current game object has the purple teddy bear sprite, or we're trying to destroy yellow teddy bears, and this game object has the yellow teddy bear sprite, those are also possibilities for finding a teddy bear that we should currently blow up. So if any of these three things are true, then we know we found a teddy bear of the color that we're trying to blow up. So we call the blow up teddy method with the current teddy bear as the argument. The blow up teddy bear method is pretty simple. All I do is I instantiate the explosion prefab and I destroy that teddy bear. So that's the heavy lifting for making it so we can destroy teddy bears of different colors based on player input.
To recap, in this lecture you learned how we can selectively process game objects in our game using a list and a for loop. And you also learned that if we're going to remove elements from the list as we're navigating or iterating over that list, we can't use a for each loop, and we also can't use a forward for loop. We need to use a backwards for loop to make sure we don't skip over any of the elements that should be removed from the list. In this lecture, we're going to keep blowing up teddy bears, but this time we'll use a list, a for loop, and tags to simplify our code. Let's get to work.
As a reminder, we learned about tags in Unity when we did the tagged destruction lecture in the selection module. The main camera is by default tagged with the main camera tag, and our prefabs have not been tagged at all. So the explosion prefab isn't tagged and the teddy bear prefab isn't tagged. Remember, we can see the tags we have available to us by going to Edit, Project Settings, Tags and Layers, and expanding tags if you need to. And as you can see, I've already added green, purple, and yellow tags. And we're going to use tags to make our code much more efficient when we blow up teddy bears. Let's look at the blowing up teddy script. I have the same fields that I had before, but my update method is much simpler than it was before. Now I'm just checking to see if I have input on the blow up yellow teddies input axis, and if I do, I call blow up teddies with my yellow teddy color. And I do the same for blowing up green teddies and blowing up purple teddies. As before, I have just if statements here, no else ifs or elses, so that I can blow up multiple colors on the same frame. My blow up teddies code is much simpler than it was before. Instead of needing to check each game object in the scene first to see if it has a sprite renderer and then to see if it has the appropriate color, all I need to do now is the following. I still need to clear my game objects list, and this time, instead of finding all the game objects in the scene, I'm going to find game objects with a specific tag. And the tag I'm going to look for is the color that was passed in up here, which is the teddy color enumeration. And tags are actually strings, not the teddy color enumeration. So I have to take that enumeration value and convert it to a string by calling the toString method on it. So this is a string that's either green, purple, or yellow. And then I find all the game objects that have been tagged green, purple, or yellow. And then I add all those elements of that array to my game objects list using the addRange method. But now my game objects list only contains game objects that are the color that I'm trying to blow up. So I do my backwards for loop, blowing up each element of that list, and blow up teddy stays the same. So this code has been greatly simplified by using tags. We have one more piece to look at though. When we looked at the teddy bear prefab in the Unity editor, it didn't have a tag, so how is it getting a tag? Well, I actually also showed you this in the tag destruction lecture. So in our teddy bear spawner script, when I spawn a teddy bear, when I set the sprite to a random sprite, I also set the tag. So here I've spawned the teddy bear and saved that new game object. I've moved it to world position, I got its sprite renderer, and based on the random number I generated, I've set its sprite to a particular color. Or I've set its sprite to a teddy bear sprite of a particular color. Now I'm going to add a tag to this teddy bear game object, and I'm going to take teddyColor.green, which is the enumeration value green in the teddy color enumeration. As I mentioned when we were looking at the blowing up teddy script, tags are strings, not enumerations, so I need to convert this to a string. And this line of code adds the green tag to the teddy bear I just instantiated and gave the green sprite. And I do similar things for purple and for yellow. So the teddy bear spawner, when it randomly picks a teddy bear color sprite to apply to the newly spawned teddy bear, it also adds a tag of the appropriate color. And then in the blowing up teddy script, we use those tags to find the teddy bears that we want to blow up based on a particular input from the player.
To recap, in this lecture we refactored our project from the previous lecture to use tags to simplify our code. In this lecture, we'll revisit our Ted the Collector game to make it a little more interesting using a list and iteration. Let's go check it out.
I've changed the functionality in this game by what appears to be just a little bit, but it actually leads to a whole bunch of code changes. I'll start by showing you how the game works now. I still right-click to place Dr. T heads, and I still click the teddy bear with the left mouse button to make it start collecting, but now it actually goes to the closest pickup, not the oldest pickup. And if I add pickups along the way, it will change direction and pick up those closest pickups, and then I can place more and it will go to the closest one first, and so on. The Ted the Collector code has minor changes. We save a reference to a teddy bear object because we're going to need to call a method in the teddy bear object, so we need a reference to the teddy bear.
And while I could have marked this with serialized field and populated it in the inspector, I decided I wanted to find it using its tag, so I added a teddy bear tag to the teddy bear prefab just to show another way that we've already seen when we looked at tagged destruction, but another way to actually find game objects. And I still have a list of the pickups in the game. I changed my properties, so now I don't just return a target pickup, I actually return a list of all the pickups that are currently in the scene. I've added a start method to retrieve the teddy bear game object, so I find it with its tag, and then I get the teddy bear script attached to that teddy bear game object and put it into this teddy bear field. So just as a reminder, we've used getComponent a lot to get things like the rigid body 2D and so on, but we can use getComponent to get scripts that we've attached to game objects as well, because remember, scripts are just components like all the other components we have. In Update, when the player presses the right mouse button, we do all the things we did before, but we also call this new method in the teddy bear that has the teddy bear update its target. And this is the method that we'll take a look at that makes it so the teddy bear can decide, I no longer should go toward my current target pickup because the new pickup that was added is closer. And that's why the teddy bear will change direction and go after a new one that we've placed that's actually closer. And remove pickup works exactly the same as it did before. We have massive changes in the teddy bear script, so these are still the same, so the same fields. In our start method, we do the same things we did before, and we do the same thing on mouse down as we did before. It looks like there aren't any changes yet because on trigger stay 2D is the same as well. But here's where things start getting different. Remember, the update target is the method that Ted the Collector calls when a new pickup has been added to the game. If our current target pickup is null, which it will be when the first pickup has been added to the game, or when we finished collecting all the pickups and then the player added another pickup to the game, we set our target to be that pickup that just got passed in. So that's an easy one. If we don't currently have a target, then this is our new target, so we set target. If we do currently have a target pickup, we have to decide if this new pickup is closer. The first thing we do is we call a getDistance method that I wrote to get the distance to our current target. That method just uses a built-in vector3 distance method to calculate the distance between two objects, the teddy bear and the pickup that I pass in as an argument to the method. So I pass in my current target to that method and I save the result in my target distance. Then I calculate the distance to the new pickup that was passed in here and check to see if it's less than target distance. Because if it is, the new pickup is closer to the teddy bear than my current target pickup. So I need to change my target. I call set target with the pickup that was passed in. To set the target, first I set my target pickup field to the pickup parameter, and then if I'm currently collecting, I go to the target pickup. I need this if statement because remember, this set target method gets called with the very first pickup also, and I don't want to just start moving toward that pickup when I set it as a target because I'm not collecting yet. I haven't been clicked on my collider, so I'm not collecting yet. So I only want to go to the target pickup when the set target is called if I'm currently collecting. And this will make it so I change direction and go to a different pickup. The go to target pickup method is exactly as it was before. The go to next pickup method is an interesting one because it sets the target pickup field to the result of calling another new method called getClosestPickup. And if the target pickup isn't null, I'll go to it, just as we've seen going to any other target pickup.
But if it is null, there are no more pickups to pick up right now, so I set the collecting flag to false. The getClosestPickup method does some interesting processing with a list and with iteration. So the first thing I do is I get the list of all the pickups in the scene right now by accessing this new property in the Ted the Collector class. I declare a couple of variables here. I want to keep track of the closest pickup, and I want to keep track of how far away I am to the closest pickup. If in fact the list of pickups was empty, then I return null. And back here in go to next pickup, remember that's why I check if it's null, because it could return null. If the list of the pickups in the game is at least one big, then I know I should walk through all the pickups and find the closest one, and that's the one that I should return from this method. I start by assuming that the first pickup in the list, the element at index 0, is the closest pickup, and I calculate the distance to that pickup. I could find out this assumption is wrong. I may walk through the rest of the list and find one that's closer, and that's great. If I do, then I'll replace this, but I can start by assuming that the 0th element in the list is actually the closest pickup. Here's where I use iteration, and I'm using a for each loop to go through the list of pickups. I will confess I could have optimized this and avoided the very first loop iteration by using a for loop that starts I at 1 rather than 0, but I just decided that that was an unimportant optimization for this particular example, so I'm using a for each loop instead. So I'm going to look at each pickup in my list of pickups. What I'm going to do is I'm going to calculate the distance to that pickup, and I'm going to see if the distance to the current pickup is less than the shortest or closest distance that I've found so far. If it's not, this pickup isn't closer than the closest pickup I've found so far, so I don't do anything. But if I did find a new closest pickup, one that's closer than the closest pickup I've found so far, I set closest pickup to pickup, and I set closest distance to distance, so that next time through the loop, closest distance has been updated to be for my current closest pickup. And I just keep going through this loop, replacing both closest pickup and closest distance as necessary as I find a closer pickup. That means that when I'm done with the loop, I've actually found the closest pickup that's in the scene right now, and that's the one that I return. This pattern of assuming the 0th element in the array or list I'm processing is that extreme value, either a minimum or a maximum, is a pretty standard pattern for looking for an extreme value, a minimum or a maximum in an array or list. So you should make sure you understand how this works so that you can use this pattern whenever you need to do it. And if you really want to do the optimization of avoiding that first loop iteration and using a for loop here instead of a for each loop, that's perfectly acceptable as well. It's still the same pattern.
To recap, in this lecture we saw another interesting use of a list and iteration in a small game. Congratulations! You made it to the end of the second course in the specialization. Great job! I know it's still hard for some of you to learn how to program and how to program in the Unity game engine, but just remember, this struggle is helping you develop your programming skills and your game development skills. If you'd like to continue exploring these topics in a structured environment, you should move on to the next course in the specialization, which is called C# Class Development. But if you've had enough of the structured environment and you want to just go off and develop games, you should go do that instead. No matter what, thank you for taking this course. I really love doing these courses on Coursera, and I appreciate that you joined me on this journey of exploration in both C# and the Unity game engine. Cheers!